So good morning, everyone, to this mini colloquium on plasmonic metamaterials from surfaces to 3D supercrystals. This is part of the CMD 2020 GEFES conference. And my name is Arantxa Fraile Rodriguez from the University of Barcelona, who I'm organizing this workshop together with José Ángel Sánchez Gil, Jaime Gómez Rivas, and Antonio García Martín. So this mini colloquium will have two sessions, the first one today and the next one tomorrow at the same time. And and in today's session, we will have a series of talks, some invited talks and contributed talks. So the outline of the program is listed here. And we would, before commenting on the speakers, just a few guidelines. So as the invited talks will be about 30 minutes. They have the participants 30 minutes for the contributions and 10 minutes for questions. And the contributed talks will be 15 minutes plus 5 minutes for questions. For all of you, those who would like to ask questions, there are two ways. Let's say one way is to use the chat. I strongly encourage this. So you can write your questions at any time during the talk, because then I would simply collect them there. And then, I can either later on at the end of the talk pass them directly to the speakers, and they can so read them, and then the speakers can answer. Or alternatively, you can ask them at the end of the session, or you can raise your hand using the tool in Zoom at the end of the session, at the end of the talk as well. And then we can, open your microphone and ask questions. By default, your microphones would be off to avoid any interference and any noise. But as I said, again, at the end, if you would like to ask something, it could be possible that if you raise your hand, you can talk directly to the speaker. But please ask as many questions as you like, also using the chat. Let's make this lively. Also, I would like to ask you to stay until the end of the session, not only because the session is very interesting, but also because at the end, we would then switch on all of our cameras, and then we would take a picture of all the participants to the session. And this is also nice for later, no? Am I forgetting something relevant, Pablo?
No.
To mention, or?
I think it's okay.
It's okay. Then without further delay, I would like to introduce our first speaker of today. She's Isabel Pastoriza Santos from the University of Vigo in Spain. She has an invited talk. And then the title is slightly changed to adapt a bit better to the focus. And the new title is going to be Plasmonic Supercrystals as Effective Antennas for Source Sensing. It is a great pleasure to having you here. And please start whenever you want.
Thank you. So can you see my screen? Yes. Okay, so thank you for the kind presentation. As Arantxa says, I decided to change the topic of my talk because I think it's more related with the topic of the session. So I will talk about a plasmonic supercrystal for source sensing. I come from the Biomedical Research Center and the Department of Physical Chemistry at the University of Vigo. And I'm the coordinator of the colloidal chemistry group, that we are a multidisciplinary group constituted of chemists, physicists, biologists, and biochemists. We have different research interests, but mainly we are interested in the fabrication of nanomaterials, metal nanoparticles, pure and hybrid metal nanoparticles, because we are interested in their optical response. Also, we work on the preparation of or in the combination of the metals with other materials such as polymers or inorganic materials such as silica or organic frameworks. So another research line is related with the assembly of the nanoparticles, since the assembly allows us to obtain materials, nanostructure materials with enhanced or improved properties. Related with the fabrication of the nanomaterials, is the next research line that is focused on the structural and optical characterization of the materials. In these research lines also we collaborate with strong groups in order to use advanced techniques. So in terms of applications, we are focused on catalysis, but also in sensing based on localized surface plasmon resonance and surface enhanced Raman scattering. And also we are interested in bioimaging based on surface enhanced Raman scattering. So the outline of my talk today is the following. I will start with a brief introduction, just I will mention the plasmonic effects in metal nanoparticles. I will briefly introduce the surface enhanced Raman scattering, and I will talk about the different methodologies for the preparation of supercrystals. Then I will move on to results, where I will talk about the synthesis of octahedral gold nanoparticles, the fabrication of plasmonic supercrystals using microfluidics, and finally the analysis of the search performance of those plasmonic microfluidic chips for sensing. And I will finish with conclusions and acknowledgements. So probably most of you already know that when a metal nanoparticle interacts with light, there are different effects occurring at the nanoparticle surface. For instance, enhanced absorption and scattering process are generated, even also at the nanoparticle surface, really intense near electromagnetic fields or a local heating are observed. And those effects and processes can disturb the molecules that are located nearby the surface of the metal, and this can produce strong effects such as enhance certain vibrational modes, or enhance or quench the emission of certain molecules or catalytic reactions, and so on. Therefore, these effects are responsible of the multiple applications of these metal nanoparticles. The nanoparticles can be used for photothermal therapy, catalysis, imaging, for energy, and so on. But an important issue is try to design the most suitable nanoparticle for the application that we have in mind. This means try to fabricate the nanoparticle with the optimized optical response in terms of absorption or scattering contribution, the energy of the localized surface plasmon resonance, etc. In that case, we will be able to fulfill the requirements of the application that we have in mind. So since I will show you the application of the supercrystals for CERS, I just briefly introduce the surface enhanced Raman scattering, and is related with the Raman spectroscopy. And the Raman spectroscopy is not an analytical tool. The sensitivity is very low because the Raman spectroscopy is based on the electrons that are scattered inelastically when a molecule is irradiated with light. But if we see here, just 1 in 10 to 8 incident photons are scattered inelastically. But last century, in the 70s, it was found that by Fleischmann that the vibrational modes of a pyridine were enhanced when the pyridine absorbed on a rough silver film. Fleischmann explained that effect due to the large absorption of the molecules on the silver film. Nevertheless, later was found that by Dwight and Creighton that the mechanisms involved in the Raman scattering are two. One is related with the near electromagnetic fields generated around the nanoparticles when they are excited, and another effect is the chemical mechanisms that is related with electron transfer occurring between the molecule and the metal. So we know that individual meta-nanoparticle can enhance the Raman signal of a molecule between 10 to 6, 10 to 8, but this enhancement can be even higher in the case of having cell nanoparticles, cell assembly of nanoparticles, and this is because of the formation of what is called hot spots. This means huge electromagnetic fields that they are generated at the gaps between the nanoparticles. Imagine if we are able to locate the nanoparticle or the molecule in the gap, we were able to enhance the Raman signal. In the case of the having hot spots, the enhancement factor can be even 3 orders of magnitude larger than in the case of an individual nanoparticle. But the point is that if we think in assembly, the nanoparticles can be randomly distributed or well ordered. And the point that Javier Garcia Dabajo and Luis Marzan some years ago studied both situations and observed that the behavior in terms of search enhancement was completely different. So they simulate an assembly of randomly distributed cold nanorod, and in this case what they observed, this is a video of the search enhancement, what they observe is that when we move from the surface of the cell assembly deeper inside of the assembly, the intensity of the hot spots, that meaning the intensity of the search signals decrease till completely decayed. Nevertheless, the situation in the case of a supercrystal is completely different. So in that case, what they observe is that when they are illuminated with light, in that case, there is like propagation modes that form standing waves, and these standing waves form like areas with a really strong hotspots or a really strong source signal, and these areas appears at a different resonant depths in the supercrystals, and there is not a really decay in the search signal when we move inside of the supercrystal. Therefore, for search sensing is very nice to try to fabricate plasmonic supercrystals. Indeed, several authors report the high sensitivity of these plasmonic supercrystals. So there are like different methodologies to obtain supercrystals, but probably the most commonly used is the drop casting. In the case of the drop casting, is just putting a drop of the colloidal dispersion and let the solvent evaporate. In that case, the evaporation of the solvent is controlled through kinetic and thermodynamic factors, but the point is that after the evaporation, just small areas or volumes are forming supercrystals, and even the reproducibility of the supercrystals is very low. Therefore, in the last years, a new technology to prepare supercrystals has emerged, and this is the stamping. It's just use a polymer mask to stamp on a colloidal dispersion the supercrystals. In that case, the quality of the supercrystals is very good, but the point is the limitation is the size of the supercrystal that is limited to a few microns. Another technology or methodology to obtain supercrystals also reported in the literature is related with the assembly of the nanoparticles in a colloidal dispersion. So in that case, the assembly is induced by the ligands that are at the nanoparticle surface. For instance, in this example here is the case of the ensemble induced by a complementary DNA strands. So in our case, we are using microfluidics to obtain the supercrystals, and I will show you, since this technique had been used previously to assembly other colloidal systems. And I will show you in the next slides. So I will now start with the results. First, I will briefly show you the preparation of gold octahedra that will be the nanoparticles chosen for prepare the supercrystals. And we have chosen the gold octahedra because we are able to obtain the nanoparticles uniformly, and also because they present edges, sharp edges and tips, and this is nice for produce hot spots. So the preparation is a seeded growth method where we start with gold nanorods. Using butanoic acid, we reduce a gold precursor selectively on the nanoparticle surface in order to obtain the octahedra. This is the evolution of the particles, and the nice thing of this approach is just by modulating the molar ratio between the gold nanorods and the gold salt precursor, we are able to modulate the size. Indeed, we are able to tune the size from 30 nanometers to more than 150 nanometers in side length of the gold octahedra. And this allows us to modulate also the optical response, as you can see here in this graph. So the particles are ready. So the next step is try to assemble, and therefore we have decided to use microfluidics because of the advantage of this technology. So the first step was the preparation of the microfluidic channels using soft lithography. The polymer is PDMS. This is a skin of the channel, and you see that it's around 1 centimeter length, 10 microns height. The end is closed, and also we have punch and inlet for the injection of the nanoparticles. Also, it's important this part here. This is in this part the PDMS film is very thin. That is fundamental for to induce the assembly of the nanoparticles, because the next step is take the gold octahedra. These nanoparticles are 75 nanometers inside length, and we prepare a colloidal dispersion very concentrated with the right concentration of the surfactant. This is a very important point. And using a pump, we just inject it into the microchannel, and this will produce the evaporation of the solvent through this PDMS film, and the flow of the nanoparticles to the end of the microchannel, and with the nucleation and growth of the supercrystal. So then we peel off the PDMS film in order to analyze the supercrystal, and this is a top view of the nanostructure obtained by scanning electron microscopy. If we make a zoom, we observe the nanoparticles close pack with order. Even here is the fast Fourier transform when we observe the pattern that is typically from ordered crystals. So if we make or if we obtain a tilt image, we can obtain the thickness or the height of this supercrystal, which is around 10 microns, which corresponds with the height of our microchannel. So in principle, the supercrystals resemble the dimensions and the morphology of the microchannels design. So and the point is that, as explained previously, the most intense areas for sensing are located inside the supercrystals. So therefore, we are very interested to know how is the structure of this material in the interior. So for characterize that, we use focus ion beam combined with scanning electron microscopy. And first we cut a supercrystal slide. This is the zoom of the slide, and then we perform a sequential milling with the FIP. And after each milling step, we took a SCN image. After finishing the milling, we took all the 2D SCN images, and we make a 3D reconstruction using a slide and view software. This is the results of the 3D reconstruction, where we can see that in the inner part of the structure, the well ordered or the particles are well ordered and close packed. So the nice thing is that we have integrated supercrystals into microfluidics, and therefore in this case we have a nanostructure material which is very sensitive for surface sensing, and on the other hand we have a microfluidic channel with several advantages, like such as allow the miniaturization, automation, and so on. Therefore, merging both technologies allow us to go a step further in the fabrication of a point-of-care sensor with high performance in terms of sensitivity, reliability, and so on. So the next slides will be related with try to analyze the performance of these microfluidic chips for surface sensing. So since we are interested in the detection in flow, we have a punch at the end of the channel and outlet. The next characterization then that we performed was check the sensing capabilities. We use as model molecule naphthalene thiol. We inject with a pump with a certain concentration, and first we check that the distribution of the molecule in the supercrystals is rather homogeneous. But the point is that we are interested check if through microfluidics we are able to infiltrate the molecule, because if we think in the other technologies like drop casting or stamping, in that case, when they are used for surface sensing, most of the time the molecule remains in the top layers of the supercrystals, and therefore cannot reach the most intense areas of the nanostructure. But we were thinking that probably since we are injecting the nanoparticle the molecules of interest in a microfluidic channel and the molecule flow, maybe we would be able to introduce or to infiltrate the molecule inside the supercrystal. So in order to check the infiltration, what we did was analysis in depth of the surge response of the supercrystals. And this is the result. These are surge mappings recorded as at certain vibrational mode of the molecule, and each map corresponds to a different height. And this is the average intensity of the surge mapping versus the height. And you can see here that there is a plateau of maximum intensity. And this plateau, if we observe here, the highest intensity signal occurs along 10 microns, and this 10 microns corresponds with the height of the supercrystals, meaning that the molecule is homogeneously distributed in the whole supercrystal. In order to understand a bit more the behavior of our supercrystals, in collaboration with Professor Taboada from the University of Extremadura and Professor Ovelleiro from the University of Vigo, we simulate the response of our supercrystals performing electromagnetic simulations using the M3 full wave solver. In that case, we calculate the near electric field enhancement, and this also allows us to obtain the surge enhancement. So, as a model system, we have used a supercrystal made of 8,200 octahedral nanoparticles with similar dimensions that those used experimentally. The first experiment or the first simulation was performed using an interparticle separation distance similar to the interparticle separation distance that we know that they are approximately in our plasmonic supercrystal. So this image here corresponds with this plane drawn in this scheme. And now, if we check the surge enhancement, these calculations were performed considering the experimental illumination conditions. We observe that the most intense signals are concentrated at the surface of the supercrystal, and this is because probably due to the penetration of the light. The light cannot penetrate really inside of the nanostructure. Nevertheless, just by increasing a bit the interparticle distance, or even increasing the interparticle distance, but also providing the nanoparticles with a certain orientation, we have randomly oriented the nanoparticles plus minus 5 degrees. In that case, what we have observed is that the light is able to penetrate, and in that case, the surge response start to be more homogeneous. In our case, the experimental results show that the surge intensity inside the supercrystals were uniform. Therefore, we can explain that behavior in terms of the presence of defects, cracks, or even particles with different orientations, or areas where the supercrystal present a different orientation. So the next, in order to test if our plasmonic microchip would be interesting for sensing, we test the limit of detection. In that case, we use crystal violet, that is a no pollutant, and we infiltrate and we test with different concentration of the molecule. And in principle, as you can see here in these search intensity maps, we are able to detect after using an infiltration time of 30 minutes up to 10 to minus 15 molar. Also, as is obvious, at large concentration, there is a uniform distribution of the molecule in the whole supercrystal, and when the number of molecules decrease, we observe that this uniformity is lower. But just by increasing the infiltration time, we are able to improve this limit of detection. For instance, we can get 10 to minus 19 molar with an infiltration time of 24 hours. Of course, this is not really practical or really good for a real application. The next step was to check the multiplex capabilities, check if we are able to detect more than one molecule at the same time. In that case, we have used as model molecules crystal violet and acid blue. Each molecule presents a specific Raman signatures. If we mix and inject in our microfluidic chip, and we analyze by search, what we observe is that in the resulting search spectra, we observe signals from crystal violet and also signals from acid blue. And even in the search intensity map, what we observe is that both molecules are homogeneously distributed. But sometimes it's very interesting to try to detect selectivity as a certain molecule. So in order to check if we were able to achieve that with our microfluidic chips, what we did was combining the microfluidic channels with microchromatography. In the case of the microchromatography, is based on the use of silica particles that they are negative charge, they are in a column, and when you pass a mix of positive and negative charge, the particles or the molecules with opposite charge are retained by the silica particles and just flow through the molecules with a negative charge. So this is the idea for provide selectivity to our sensor. Therefore, in our microfluidic channel, what we did was integrate also silica particles after the supercrystal, plasmonic supercrystal. This is the characterization of, this is the channel, this is the plasmonic supercrystal, this is the silica nanoparticles, which are cell assembly, and this is a cross section where we can see the interface between both type of assemblies. So in order now to prove the selectivity, we have select again the same molecules, crystal violet that presents positive functional groups, and the acid blue that presents negative functional groups. And when we introduce as a mixture in the microfluidic channel, what we observe is that here is the resulting spectra, and we observe just the signals corresponding to the acid blue, because the crystal violet, since is positive charge, is retained on the silica particles that they are negative. And this is also was checking by search intensity maps, and where we just can observe the acid blue on the plasmonic supercrystal region. But the nice thing is that we can make the opposite. We can detect the crystal violet instead of the acid blue by tuning the charge of the silica. This is in that case, this is the resulting spectrum where we can observe the characteristic peaks from a crystal violet. So with this, I come to the end, and I hope I could show you that the microfluidic technology is a good alternative to prepare plasmonic supercrystals. I have shown you that these supercrystals presents a very nice performance for sensing. They present very nice high sensitivity and also multiplexing capabilities, and even allows the separation of molecules by charge. Finally, the acknowledgement. I would like to acknowledge from my group, Danny, which a PhD student is involved in this project, Sergio Gomez, that is a postdoc, Jorge Perez-Justo, assistant professor, and the collaborators, Taboada and Ovelleiro, that made all the simulations, and Jack Len, that helped us with the first fabrication of these supercrystals in the microfluidic channels. And also I would like to acknowledge the funding agency and all of you for your attention. Thank you very much.
Okay, thank you very much, Isabel, for this excellent talk. So the talk is now open for questions. Everyone that would like to start, please raise a hand or say something. I don't see any questions yet here. Okay, so maybe I can start. I have a few. So in this octahedra, no, you when you look at the supercrystals in the SEM images, it looks as there could be different orientations of the octahedra, so they would fall on different facets. How, I mean, if you repeat this experiment many times, does it happen all the time like this, or can you somehow control, you know, on which facets they fall, or to have more homogeneous or less homogeneous supercrystals? Because in the simulations, of course, they all, you know, are very compact and following more or less like in a Tetris way, but in reality seems a bit different.
Yes.
Can you control this, and does it have an effect later on the cell signal, or?
In principle, it's very reproducible, and the point is that we need to consider that for doing the SEM characterization, we need to peel off the PDMS, and this also disturb the nanoparticles in the supercrystals. The point is that we are now collaborating with a group in Paris, and we are performing SACs in order to check the crystallinity of our supercrystals. And we have already evidence that the order is maintained in really large areas. Even now we are studying the kinetics of the formation of the supercrystals. But in principle, yes, I think that they are like microdomains. But in all these microdomains, there are particles probably that they have like different orders, but keeping this a well-ordered structure.
Mm-hmm. Okay. Yes, I see a question by Maria Ujue. Thank you for the nice talk. The performance of the crystals depends on the height of the channels crystal. Have you tried different sizes?
Yes, we tried different heads, different dimensions, different shapes, and in principle, the performance is similar. If, for instance, if not the height, but if the length of the thickness of the microchannel is rather large, then sometimes the supercrystals are not really good. So therefore, the microchannel has to be rather narrow. Otherwise, the quality is not good. But in height, it doesn't matter. It's not important.
Okay, thank you. And thank you, Maria Jose, for the question. Any further questions? Anybody wants the mic? No? Well, since we still have some time, I can still ask some questions.
Arantxa, I would like to ask a question.
Good.
Can you hear me?
Yes.
Okay, thank you very much for the talk, for the nice talk. I would like to ask about the reuse of the supercrystal. After a measurement, is it possible to clean the supercrystal and to get the same sensitivity?
Depends on the molecule, because if the molecule presents a strong affinity by the metal, it's not possible to remove completely the molecule. But for instance, in the case of the crystal violet that has not a strong affinity by gold, but we can use a couple of times without no problem.
Okay, thank you.
Thank you.
Any further questions? Have you done a study to check how much the cell sensitivity depends on how compact the supercrystal is? Because at some point you say, well, the molecules do not quite, well, depending on the approach, no, quite fit in, or I guess depending on the molecule in itself. But so on the one thing, one could think, well, it's good that the supercrystal is very compact, no, to increase the signal. But on the other hand, if not so many molecules can fit within the, you know, voids or cracks or whatever. So what is then, you know, how do you gain there? What is the compromise?
Yeah, the point that we need to have in mind that the nanoparticles present ligands at the surface, no? To provide colloidal stability. I didn't explain in detail, but in this case it's a surfactant. For the preparation of a well-ordered supercrystal, is very important the concentration of this surfactant. If we increase a lot the surfactant, we decrease, the order is lost. No? In order to check how important was the distance of, because the distance also determined the near electric fields at the hot spots, we were playing with lengths, with ligands of different lengths in order to control that. But the point is that we are using ligands. The point is that not all the ligands induce also the formation of the supercrystals. We test with polyethylene glycol of different sizes, and in principle, we do not observe a strong effect in the cell signal. Because at the beginning was what would be very nice, try to control the distance between particles, and in that case we can modulate the sensitivity, but it's not very easy.
Okay. Okay. So any last question? We have a couple of minutes left. No? Then maybe we leave it here. I have a few more, but I think I would probably ask you separately. Thank you again, Isabel, for your commitment to this online conference, and thank you for this nice talk. And now we move on to the next speaker. So the next speaker is, again, an invited speaker, is Maria Jose Gonzalez, who is going to talk about applications of nanocolumnar coatings with light localization properties.
Okay.
So whenever you are ready.
So, yeah, I think you can see the yes. Talk. Okay, so, well, thank you very much, Arantxa, for the introduction. And thank you very much for having invited me to this nice colloquy. And first, well, I would like to say that I think I am going to move a little bit out of the main topic of the colloquia, since when I was invited and I was said, okay, this is going to be, the title is Plasmonic Metamaterials, but actually, I don't know why I cannot advance on my, yes. Metamaterials, when I think of metamaterials, I am thinking on very ordered structures, when you look for the order in order to control the properties of your system and to enhance some properties and to design them for the application that you want. But actually, what I have been analyzing in the last years are the properties of systems that are not at all like that. They are nanocolumnar coatings that we fabricate through glancing angle deposition sputtering, magneton sputtering, and then actually they are they have like a short distance order if you want, but they are very unordered. But still they have interesting properties and some light localization properties. So this is what I am going to explain a little bit today. So the first thing I would like to do here is to say why we are doing, we are using magneton sputtering to fabricate samples. And the reason is because this is a technique that actually is able to produce high purity films. It's a technology that in principle can be scaled up. It's used in industry to produce coatings, dielectric coatings for windows, for example, or for many other applications. And if you do this in a tilted deposition, you can obtain nanostructures. So it's a nice method to obtain nanostructures, but in a simple and affordable and cost-effective way. So what is this glancing angle deposition? In this case, what we are talking here is that, okay, this is a sputtering where we are going to deposit a coat, a substrate, by extracting the material from the target, but instead of having the target and the substrate as usually, sorry, yes, instead of having them just face to face, what we are going to do is that we are going to have the substrate tilted with respect to the target, and in this case, the flux of atoms that arrive here is going to arrive with a tilt angle. And like you can see here in the sketch, in this case, what is going to happen is that the atoms that are atoms that arrive to the substrate are going to make a shadow in that region, and the next atoms are going to be then being deposited, forming nanocolumns. And this is a simple way to obtain nanocolumns. Of course, the process is a little bit more complex than that, because you need to take into account that because we are talking about sputtering, we have an argon gas for making the plasma in order to extract the atoms from the target, and this is going to make collisions with the atoms that we are trying to deposit, and this is going to change the angles, so we are not going to have this so directional effect to have the shadowing and the nanocolumn. So there is a balance between the pressure of the plasma and how we can deposit this on the substrate, and so we can play with the different conditions here. So when we play with all these conditions, actually there is a huge amount of parameters that can allow us to modify the morphology of these nanocolumns and the kind of structures that we can obtain. So for example, as an example here, what I saw is the gold nanocolumns, a gold coating that has been done by fixing the angle between the substrate and the target at 85 degrees. And we have changed, this is fixed, but we have changed the argon pressure, and it's increasing. And as you see, we go from very tilted columns to less tilted and a much more compact structure when the pressure is higher, and then there is less directionality. So once this, we have been analyzing the properties, the optical properties of several of the films that we can obtain with this technique. And for example, one of the first cases that we studied was the case of obtaining gold nanocolumns, but in principle, what we were doing is we were depositing with the tilted angle, but while the deposition was being done, we were rotating the substrate, okay? In this way, what happens is that what we are growing tilted nanocolumns, but as we are changing the orientation continuously because we rotate the substrate, what we are getting at the end are vertical columns. We cannot at the end obtain the vertical columns as the one that are shown here. So what we realize while doing this is that depending on the angle, the tilt angle, the deposition angle, we could be able to obtain very dark gold coatings. So at 75 degrees, for example, we got a gold layer, a little bit dark, of course, because it's not flat, it's full of columns, is very nanostructured. But at 87 degrees, what we were getting was a very dark, almost film. Okay, so and the morphology of the two different films is slightly different. Here we can see that we have smaller nanocolumns here, and in the other case we have bigger ones. But the first thing we checked then is trying to understand or to link this different in the optical properties with the differences in the morphology. And what we could see is that the bigger the deposition angle, what we could see is that the nanocolumns had much narrower distribution in the diameter and they were smaller. And on the other hand, when the deposition angle was bigger, then we had broader distribution of the diameters of the nanoparticles. And what we can also see is that for the smaller angles, the density of nanostructures was smaller. So we were getting less nanoparticles, they were higher, and they were more uniform in the height, and they were also more broadly distribution in diameter. And in the other case, we were having this much more distributed or narrow distribution in diameters, but on the other hand, they were much more inhomogeneous in terms of the height. So just as we could expect, when we look at just by looking the color of the samples, when we measure the reflectivity of the sample that was done at the high angle, we could see that actually the values of the reflectivity were very low in all the visible spectra. And in the case of the fields deposited at higher angle, we see that still the reflectivity is low compared with a thin field, but the values were higher. So these films are very inhomogeneous, so it's difficult to be able to do the simulations or to provide an interpretation or an analysis, because it's full of nanocolumns of different sizes, diameters, and everything. But what we understood from these things is that actually what is going on here is that we have nanocolumns that have then the plasmonic, they have localized plasmons, and when we are having the system with a more narrower distribution in diameters, but with a much higher distribution in heights, what is favored here is the light trapping. We have much more phenomena of multiple scattering, which at the end give rise to a much higher absorption of the light, and this is how we have the much dark, almost the black gold here. And in this case, because the nanocolumns are more homogeneous, and also in the height they are more homogeneous in height. We don't have as high light trapping, is not as efficient here. And well, we checked that this was not depending also on having always the silicon substrate. We could also have obtained the same kind of behavior, the dark behavior with a high angle in a transparent substrate, just in case we need it. And well, this is a very, very simple way of obtaining a black metal coating that can be used in several applications in order to get heat exchangers, absorbers, and these kind of things. And this, we see, okay, these are the black, dark black coating, and we associate this to the plasmons, but we can also get with the nanocolumns systems that are not dark, and they should also have the plasmons. And in this case, we are not enhancing so much the absorbance, we are not killing the light. So maybe we could also try to see if these nanocolumns can be used for something, for some applications, classical applications from Plasmonic, as Isabel explained before. One of the most analyzed properties of the plasmons, and one of the most desired ones, is the surface enhanced Raman scattering, because it's very useful for sensing. So we thought that maybe with the nanocolumns we could also get some interesting behavior in terms of shares. But in this case, of course, we were not looking for that black gold, we were looking bright gold. And so we did it without rotating the substrate. In this case, we used the high angle, but the substrates were fixed in such a way that in this case we were obtaining well-defined and tilted columns, tilted regarding to the substrate. So we fabricated two kind of samples. One were samples where the nanocolumns were around 50 nanometers high and diameters around 36 nanometers, and others were longer. They were double, 100 nanometers nanocolumns. And then because the nanocolumns, when you start to grow them more time, then they also broaden in diameter. Here you see they are 44 nanometers, and also the dispersion is bigger. But the tilt is the same in the two cases. That doesn't change. And so we try to see if which were the optical properties and if these kind of coatings were interesting for shares. Well, so first thing was to get an idea of the properties I already mentioned before, but we did the analysis from the images to have an idea of the diameters and the distribution, because this will allow us to have a FDTD model, simple one, but to try to understand a little bit the optical properties of the system. So we simulated the nanocolumns as being this, these structures here with the inclination, the length, and the diameter we obtained from the SEM characterization. And well, the first we tried to reproduce the reflectance of our system with the simulations. And as you can see here, this purple line is the experimental data, and the red and polarized one. And the red one is the FDTD simulation also for unpolarized light. And you see that the results are not so different. So we think we can get a little bit an insight on the behavior of our structures using our FDTD simulations. So as I said, we were trying here to know about the possibility of having some SERS enhancement with these very simply fabricated coatings. And so if you have SERS enhancement, as Isabel just introduced me very nicely in the previous talk, what you need is to have some areas where you have a field enhancement, what they are also called hotspots. So with scanning near field optical microscopy, by scanning a tip on top of the the surfaces, what we did is to try to characterize these hotspots, these points where we had a stronger feed. So here you can see the morphologies of the short nanocolumns, the 50 nanometers, the 100 nanometer long length, and here you can see sometimes in between gaps of nanocolumns, you can see that we have spots of high intensity of the field, which means that we have these areas where we have this concentrated electromagnetic field that could be interesting then to provide a surface Raman enhancement. And the measurements could be performed only at 633 wavelength, but nanometers wavelength. But in the simulations, what we did was to try to see the dependence of this enhancement with the wavelength, because usually when you can design, for example, stars or nanoparticles for cells with a very strong field enhancement, they have a resonance in a very well-defined wavelength, so the cells works very well at that wavelength. But this will be a much more broad spectrum system because we have so many different interactions and nanocolumns of different size. So we tried to see what was if the spectral response was actually much more broadband in that sense. So what we saw from the simulations is that we had the value of the enhancements increased as the wavelength increased actually, and also it increased with the length of the nanocolumns. And this increased on enhancement with the increase on the wavelength, we understand because in this case, we are having a very strong interacting plasmons between the different nanocolumns because they are very close one to the other. And so this makes that we have a redshift of the behavior. And well, here this is a more compact plot of the position of the field enhancement regarding to the wavelength. Here you can see the wavelength, and the brighter points are the ones where we have higher enhancement, of course. So you see that in both cases, in short and long nanocolumns, the enhancement is bigger for bigger wavelengths. And in order then to really see if this was useful to enhance the Raman spectra, we did it. We performed some spectra for crystal violet, and we had as a control the spectra on silicon and the spectra on top of gold. But here you can see that the spectra we obtained on top of the short and the long nanocolumns, you can really see the features of the molecule much clearer. So we are really having an enhancement compared to the pure silicon or flat gold. So the system is actually working, and we did an estimation of the enhancement we were obtaining that is not so easy to do because it's difficult to calculate how many molecules are really getting inside on top the nanocolumns and getting there, but more or less we could estimate that for the short nanocolumns we had 10 to the 3 enhancement in the lower wave, and for the long it was an order of magnitude bigger for the long ones. So I know these values are not so high, as high as the ones that you can obtain with the supercrystals or with the special nanostructures that have been designed to enhance the cells, but this is just the surfaces that can be obtained in a very simple way, and maybe for very basic or very standard applications could be useful because you can fabricate a very large area of these samples, and they also are very interesting in different wavelengths. And well, and now I'm going to change the topic, and the final application that we have for our we have been analyzing for our nanocolumns is the incorporation in perovskite solar cells. And well, as you probably know, the perovskite solar cells are one of the emerging solar cells. This is this line. I have this graph cleaner here so that you can see them, and they are very promising, and their efficiency has been increasing in the last years, but they have a problem of stability. So the generic structure of perovskite solar cells, and one of the facts that they are so interesting is because they are very simple to fabricate. You have your transparent conducting oxide and an electron transport layer that usually is titanium dioxide. You deposit the perovskite. It can be done with a spin coating, and then on top of that you spin coat also a whole transport layer and then an electrode. So it's very simple. They will be very cheap, but the main problem is that they are very unstable to the presence of water and oxygen. So because we had one of the most used layers for the electron conducting layer is the titanium dioxide, we thought that why not to put titanium dioxide nanocolumns in that part, introduce titanium oxide nanocolumns here in such a way that with them we could enhance the scattering of the light and then increase the absorption of the light inside the perovskite, so to increase the efficiency of our system. So we cannot directly deposit the titanium dioxide oxide nanocolumns in our system because we only have metals, but what we did was to deposit titanium nanocolumns, and I wanted to show this image because I think these nanocolumns are so beautiful. But then what we did was an annealing at 500 degrees, and we were able to oxidize the nanocolumns, and we were we monitored the oxidation by looking at the X-ray diffraction peaks, and we saw how the metallic titanium peak disappeared and the peaks corresponding to the oxide phases appeared there. So actually in order to have a fair comparison and to have the cells, the solar cells in the same conditions all the time, what we did is in the same substrate, we had half of the cell was with the regular structure with a compact titanium layer here, perovskite, and in the other half, only the other half, we deposited the titanium and then oxidized to the titanium nanocolumns, and then on top of this, we fabricated 2 solar cells. And the first thing was to check that the quality of the perovskite on top of the compact titania or the nanostructured titania was the same. And as you can see here, yes, we can get a good quality crystal perovskite in the 2 cases. The quality was good. And indeed, the quality of the red graph is with the nanocolumns, and you see even more peaks in the X-ray diffraction spectra, which means that the crystalline quality was even bigger, which we think could be because the perovskite was infiltrating within the nanocolumns, and this was generating crystallization points, and this was helping to even get a better structure for the perovskite. So that was helpful. And the other important property we found here is that when we measure the absorbance of the perovskite, it was also bigger with the presence of the nanocolumns. So we see as a first good point, maybe because the quality is a little bit better, but also maybe because we have this scattering effect, because we have nanostructures that we are modifying the optical properties, and then we are increasing we are not modifying, we are getting more scattering, and then we are increasing the absorbance of the perovskite. So in order to check this, what we did was on top of some nanocolumns, before putting the perovskite, we perform again some SNOM characterization. And this time what we did was to illuminate the area without and with nanocolumns, and we scan with a tip, with a fluorescent nanoparticle at the end of the tip, and then the fluorescence of this nanoparticle will be higher when we have a bigger electromagnetic field. So what we did was to scan on top, this will be just the topography, on top of the flat area, the compact titania. And as you see, the SNOM signal is very homogeneous. The intensity, the average intensity is flat. No, the intensity is flat, and this is the average, sorry. And in the case of the nanocolumns, here what you see is a much more modulated distribution of the intensity of the electric field. As you can see here, we have points where we have a high enhancement of the field, and actually, if you compare here the profiles, for example, you see that we have points where the intensity is much higher than the average, but even the average is higher than in the other case. So we see that the presence of the nanostructure is already generating points of enhancement that could help also to increase the efficiency, the absorption of the perovskite. And this could be also an explanation of the higher absorbance that we got before. I'm not going to go into too many details here because some of them I don't even understand properly, but all the performance of the solar cells was measured with and without the nanocolumns. And we saw that the efficiency, the photoconversion efficiency of our system was slightly better than 16% in the case of the sample containing nanocolumns, 15 without the nanocolumns. So we were able to increase 1% with the nanocolumns. And I know that 1% sounds very low, but when we are talking about solar cells, the increases in 1% are very good. Still, this is far from the record now for the perovskite, but this was a very simple try, and we saw that the nanocolumns were increasing the performance of the system. But the result that was very interesting here was that, as I told you, one of the most important problems of this kind of solar cells is the stability. And we, of course, measure the stability. We measure the performance of the system through 3 months. We were measuring the values of the efficiency every 15 days, every 30 days. And the ones with nanocolumns, we saw that actually were quite stable. Well, they degrade a little bit, but not much. While the ones without nanocolumns were degrading much more. So one of the most interesting results here was the fact that adding the nanocolumns was favoring a more stable cell with the time. And one of the reasons for this is when we measured the properties of the nanocolumns, the absorbance in the UV, sorry, I am very sorry. It's very difficult for me to talk without seeing the faces of the people. And so I don't know what I'm doing. Sorry. Okay, so we measure the absorption of the system without the deposition of the perovskite, the absorption of the nanocolumns coating, and with, I mean, the titanium nanostructure and non-nanostructure. And what we saw was that actually let me see if I am able to do this. Yes, this will be the FTO and this will be the control. Okay, so the control is the compact titanium layer. So you see that we have a strong absorption here. I mean that there is a lot of light going through in this UV region. But when we put the nanoparticles, the nanocolumns there, this is shifted, this absorption. And we think that this, the fact that here we are limiting the absorption of this light is protecting somehow our the perovskite from degradation. And I mean, so, well, I would like to acknowledge, I mean, this works has been done in collaboration with a lot of different groups in the black gold coatings in order to understand all the mechanisms for the growth. We were working with Rafael and Alvarez and Alberto Palmero from Sevilla. And the perovskite solar cells work was done in collaboration with our colleagues from the Laboratory of Physics and Material Structure from Paris, Lionel Egui and Suojin Chen, and Selu Wu, that is doing the PhD on this topic, and also for getting the oxidation of the nanocolumns, Fernando Fresno from Indea Energy. And for the analysis of the near field enhancement, we work with Ovidio, Antonio, Raquel González y Pablo Díaz from the Escuela de Ingenieros Eléctricos de la Politécnica de Madrid, and the snow measurements were done in Oviedo by Pablo Alonso, Javier Martín, and Javier Taboada. And I think this is all. Thank you very much.
Thank you very much, Maria, for your very nice talk. I totally understand that it's difficult to concentrate, not seeing more than a screen. It happens to all of us, I think. So it's time for questions. We have one question in the chat. This is from Jose Ángel Sánchez Gil. So I read, nice talk, Mariao. One question about the SERS enhancement factors. If I got it right, these are larger at shorter wavelengths. However, it seemed to be larger in the calculations at about 785 nanometers. Any explanation?
Well, yes, actually here, the reason is that there is a resonance. Also depend on the properties of the molecules you want to sense. And we were comparing all the time the same molecule, but this molecule has a resonance close to the lower wavelengths, which makes that it's going to provide you a bigger enhancement. And in the high wavelengths, we are out of that resonance, so the signal, let's say the base signal is going to be lower. So that's the reason. But in order to make a much fair comparison, we should have adapted molecules regarding the different wavelengths, but that was much more complex. So I don't know if I explain it clearly, but it's a question also of how much light the molecules is going to absorb from the source, the light source wavelength. If the molecule is going to be able to absorb more, then it will be able to provide also more signal. And this happens more in the lower wavelength case. And then you need to enhance. Yes, sorry.
No, go ahead, sorry.
No, I was, and then because here you are going to have like two factors, like how much light you can put in your system, and then how much shift you are going in the Raman spectra and how efficient this is going to be in order to shift and get more signal. But if our system is like we first have a system with already gets more light, even if this is more efficient, then you go like that. You see, like from this, you go up because you started from higher value, and from this, you were in a lower value, and then even if the jump is better, the final result is a bit lower. That is what we think was going on there because of the resonances of the crystal violet in absorption.
Okay, Jose says, thank you, perfect. And we have another question from Isabel Pastoriza Santos. Congratulations for the nice talk. For SERS, silver could be a better option. Have you tested it?
No, actually we didn't, because gold nanocolumns were very easy to obtain. I mean, we just tilted the angle, deposited, and got the nanocolumns coatings with the glad spattering thing. And we said, okay, let's do silver. And we started to do silver and nothing worked. Silver was very critical, and we were thinking, but what's going on? And actually, due to the diffusion of the atoms and all these complex mechanisms going on during growth, in order to grow silver, now we have learned, but you need to put a collimator to be much more sure that the angles of the atoms when you go to your substrate go better. So getting the silver nanocolumns is more difficult, and they are less stable too. So that's why we did this work with the gold, because at that time we were unable to obtain silver nanocolumns. We were getting porous fields, but not nanocolumns. But now we know how to fabricate silver. We have learned, so maybe we could try.
Mm-hmm.
Thank you
for the answer. Are there any further questions? I don't see any in the chat. Any hands? No? Then I would maybe take this couple of minutes that are left to the opportunity to ask a question myself. I remember one slide in which you showed some SNOM images of this gold in the first part of the talk. And then in the SNOM, the hotspots seem to be located really around the shell, very much at the surface. Yeah, that one. Well, these are the simulations, but the experiment as well. So the question is, actually, it seems to be more prominent in the simulations, but anyway, it's part of the question. The fact that the hotspots are located in the shell is something intrinsic to this nano column in itself, or is something related with the depth sensitivity of the SNOM technique? I don't know whether I explained myself correctly. So
you mean in the outer part of the columns?
Yes.
Oh, yeah, well, I mean, one of the things, of course, is always that we cannot, with the SNOM, we cannot go inside.
What is the depth sensitivity? I'm not really so familiar with SNOM. What is the depth sensitivity at these wavelengths typically?
Well, because we have the solid layer, the gold there, you can, usually what you do is you decide a height, and then you stay all the time at the same height to don't have too many artifacts. So, and usually you need to measure like 10, 20 nanometers from the surface, because if not, you risk to crash your tip and everything. So you are not really trying to go inside, or at least not too much. You can see these are topography signals that are taken simultaneously, and you don't really try to resolve the gaps there or anything, because yeah, that will be very dangerous for the tips, and you want to have more or less the same tip to be reproducible between all the images. So no, actually, I don't have the vertical. We also have some simulations for the vertical case, where you could see also that the light is concentrated in around, or maybe
it's there, no? If we think.
Yeah, here you can see, because okay, that will be okay. This will be the width of the nanocolumns. Okay, that will be the substrate. That is nothing, but you see, like the light is concentrated here, and then it goes down. So you will still have enhancement in around 40, 30 nanometers, 20, 30 nanometers from the surface. And this is inside. Okay, but with the calculations, you can go inside. This is the gold. There is no, you cannot put the light inside the gold. You see the light that is here. But with the tip, in the real experiment, we are not going here. We are just staying on top of the system.
Okay, thank you. Is there any last question? No? So if there is none, then thank you again for your talk. Very nice.
Thank you.
And thank you for your commitment to this online conference. I know it's not easy. Thank you very much.
It's fine. Thank you.
Sorry, I was just looking at the chat, and there is one more question, but we will move on. But Mariau, have a look to the chat, and maybe you can discuss directly about this this question. So with this, I would like to move on the next talk. This is a contributed talk by Amilcar Labarta from the University of Barcelona, who is going to talk about collective plasmonic modes in hexagonal arrays of gold nanoelements. Amilcar, it's all yours.
Okay, thank you, Arantxa. Just a second, please. Okay, thank you for the presentation. Today I'm going to talk about the collective plasmonic modes that we can observe in arrays of gold nanoelements based on the triangular lattice. In fact, we want to exploit the threefold symmetry of these triangular lattices in order to induce some kind of frustration, of geometrical frustration, on the excitation of near-field interactions. This work is inspired in the nice effects that you can find in magnetism due to geometrical frustration. You know, the case of the spin ices and whatever, where you can observe long time relaxations and energy landscapes which are really complicated. Okay, so we want to explore this occurrence of new phenomena in plasmonics due to this geometrical frustration, let's say. Okay, most of the results, well, practically all of the results that I am going to show you are from simulations. In the next talk, Javier Rodriguez is going to present some applications of these lattices. So he's going to show you the manufacturing of the samples and a specific application for surface enhancement Raman spectroscopy. Okay, so you know that when we have two elements in close proximity, there is a strong interaction between them, and then we have near-field interactions, and these near-field interactions produce hotspots, like in a bow tie nanoantenna. And this kind of excitations corresponds in general to low energies, so they are located at the near infrared, and they are associated with broadband peaks. But when we have many of these elements arranged in a lattice with translational symmetry, we have an additional ways of excitation, a kind of collective excitations, which is just the constructive interference between the excitation of each of the elements in the lattice. In this case, the peaks associated are much narrower, so they are, let's say, more suitable for applications. If you want to have a specific wavelength and not to get a broadband situation, and you want to get high absorption, for instance. Here, an example of one of these excitation in a simple lattice, which is a honeycomb lattice of dots. Okay, so we want to take advantage of this threefold symmetry of arrays of gold nanoelements based on a triangular lattice in order to hinder the excitation of the near field excitation of the near field modes. The idea is to transfer this energy or to favor the excitation of the collective modes, okay, which correspond to sharper and narrower peaks. So our main point is just to use this threefold, the fact that the threefold symmetry is not fully compatible with an even number of poles, which are the usual situation when we have a near field excitation between elements which are in close proximity, okay? So let me show you my first example. Before that, we are going to use this metal insulator metal stacking in order to favor the occurrence of Fabry-Perot modes. These modes with high absorption, low emissivity, and low de-excitation times, okay? So the general structure of the systems that I am going to show you are this one. The active plasmonic structure is grown on top. Then there is a separator in the middle, which is an insulator. And above, there is a continuous layer of gold that acts as a mirror, okay? The thickness of this layer is thick enough as to ensure no transmission. At least this is the schematic of the first systems that I am going to show you. Okay, this is my first example, and I am going to use this example to show you how the threefold symmetry hampers the common usual near field excitation of the elements. This is a honeycomb array of bars but the bars are not touching each other. There is a small gap between them, and this small gap is intended to absorb energy from the incoming radiation in the form of the near-field excitation. And the idea is if this near-field excitation is not really fulfilled in the lattice, this energy could be transferred to another mode, which could be these collective modes, okay? So if we look at the absorption, this is the absorption for this lattice. Here you can see 3 curves. Each of one corresponds to a different length of the bar, but keeping constant the pitch. So the the 2 peaks that are changing with the length of the bars are those related to the near-field interactions. And the one which isn't changed when we are varying the length of the bars is the one which depends only on the pitch. So it's the one related with the collective excitation. Let's say something like a Bragg reflection of the lattice, okay? Here, there is the electric field distribution, the distribution of the modulus of the electric field and the charge distribution corresponding to the first peak. And if we zoom these images, you can see that the charge distribution in the 3 bars that are converging at a vertex is not exactly what we can expect for a simple dipolar excitation, because we have 2 bars with a negative charge and only a single bar with positive charge. This is something similar what happens in a in a spin ice, no? You know, in a spin ice, the spins that are converging in a point can have only 2 polarities, and there is an even number of spins converging in this point, so you have always a different number of spin up and a spin down converging in the point, and this is important to determine the properties of the spin ice. So this is something equivalent here, and if you look at the electron field distribution, you can see that it's not a twofold distribution, so it's not what you can expect for a simple dipolar excitation. The second peak related to near field interaction is this one that labeled with the 2 letters, and this is also a near field interaction. It's a more complex interaction because we have a multipolar excitation of the bar, but essentially we have an interaction between the bars which are converging in the vertex. Okay, and let me show you what happens in the 3rd peak, the one which is related with the collective mode. In this case, the electric field is much more distributed around throughout the whole surface, as you can see. So these kind of modes could be interesting if you want to use the whole surface as a way to excite or detect something, because you have a large enhancement of the, you have a moderate enhancement of the electric field, but in a large area. So this is the opposite strategy of getting a hot spot. Of course, this is not exactly a hot spot. Here you can have enhancement of the electrical field of 1, 2, 3, 10, or something like that, but in large areas. Okay. So this is my first example, and let me show you another example. Here we have asterisk in a triangular lattice, and the origin of geometric frustration in this case is just the competition between the three sublattices, triangular sublattices that the gaps form. And you have these three triangular sublattices of gaps. They are rotated 60 degrees with respect to each other, so there are certain competition between these dipolar polarization of the gaps in such a way that the full ferroelectric polarization of the gaps it cannot be fulfilled. And this is the origin of the geometric frustration in this case for the near field interactions, okay? I'm not going to enter in details about the optical response. There is something similar to the previous case. We have a broad peak corresponding to near field interactions, a narrow peak corresponding to collective modes, here the electric field distribution and the charge distribution. But I am going to use this case to illustrate how the relaxation, the time relaxation of the system is. After the excitation of the system with a very short pulse of about 6 femtoseconds, we are going to study the shining of the system following the different modes of excitation. And you are going to see in the movie that I am going to show you that the system fluctuates between near field interaction that are characterized by the shining of the gaps only, and collective modes that correspond to the shining of more or less the whole surface. So here the movie, you see that the system fluctuates in a complex way between these two kinds of excitation. And there are certain times at which the full surface of the system shines. If we want to get a more quantitative idea of what happens along the excitation, we can measure the electric field in a specific point of the surface, which is this dot in the V of the asterisk. So let us measure the modulus of the electric field along the time in this point, and we can see that the electric field follows this complex. Sorry, I am going to take the marker, the laser. Okay, so you see that the electric field follows this complex fluctuations. There is a kind of modulation between two characteristic times, and which is more remarkable is the fact that the time decay is significantly longer than the duration of the excitation pulse. It's at least 1 order of magnitude longer. So these kind of systems show at least one of the properties that you can find in geometrically frustrated magnetic system, which is this long duration of the relaxation. I am going to move to another 2 examples. Now the metal insulator metal stacking is a bit different because we have substituted the continuous wall mirror by an active plasmonic layer. So here we have something like a sandwich where there are two replicas of the same active plasmonic layer, which are facing each other, and they are separated by an insulator with a certain thickness. So this is a kind of plasmonic sandwich. In this case, the active layer is just the negative version of the honeycomb lattice of bars that I have shown previously. So to manufacture this sample, we carve trenches on a continuous gold layer. These kind of systems could be useful when you can get high reflectivity and low transmission. Okay, here the absorption of this system. Look at this very sharp and narrow peak of only 11 nanometers corresponding to the collective excitation. It is very well defined, so it could be useful for application such as detection of changes in the surrounding of this structure, for instance, because you are changing the refractive index of the medium which is around. If we look at the reflectivity shows an intense dip on the position of this peak of absorption. So again, we can use the reflectivity to detect the presence of something in contact with the structure. And here, another example of a double structure. Here, the active plasmonic system is a Kagome lattice of triangles. Okay, it's worth noting that the Kagome lattice is one of the most frustrated lattices in magnetics, showing this kind of ice spin behavior and whatever. So it's a promising system, of course, worthwhile to study. Okay, so here you can see the transmission and the reflection, and you see that these two peaks are something related to collective excitations of both the active lattice on top and the active lattice on the bottom. And this is interesting because you see a dip in both. You see a dip in both the transmission and the reflection, and this is not common. And this is probably associated with a kind of dark mode in the system. The absorption shows peaks which are pretty high. Okay. And you can see also two broad peaks related to near-field interactions. Here we have two near-field interactions because we have the common near-field interactions through the gaps, but we have also a near-field interactions between the facing triangles. And in the middle, there is a kind of valley. And if you look at the range of wavelengths in the valley, you can see that the transmission is almost zero. This can be also interesting for applications to make a kind of filter. And if you want to detect something using these structures, for instance, imagine that you can detect a species which is in a liquid medium in water. You can put this water in contact with one of the structures, and then to try to detect the change in the optical properties of the structure due to the change in the refractive index of the sensing layer, due to the presence of these extra species that you want to detect. Of course, this is a proof of concept, but let me show you the transmission of this double structure of Kagome lattices. And here you have results corresponding to different values of the refractive index of the sensing layer around the value of the refractive index corresponding to water. From these curves, we can compute the intensity change percentage per refractive index unit. And you can see that there are some wavelengths at which the percentage of variation is around 200%. This is enough as to build a sensor with a very good performance. Okay. There are many parameters to optimize. For instance, we are working on this optimization of the parameters. We can change the pitch. If we change the pitch, we are changing the location of these peaks corresponding to the collective mode, and we can get higher and narrower peaks when they are not overlapping other excitations, for instance, near-field excitations and whatever. We can study, for instance, the intercalation of the two sublattices, and then we can get this kind of phenomenology here. Here we can see a very sharp variation of the transmission in a very small range of wavelengths. This could be also interesting for sensing applications. And finally, let me say that the samples, of course, we are manufacturing these samples. These samples can be manufactured by electron beam lithography. Javier will explain in more details this fabrication. And these are examples of experimental measurements on these systems, showing these narrow peaks also corresponding to collective excitation. So these hexagonal arrays of gold nanoelements can be fabricated, as I have said, by electron beam lithography. This technique shows fine tunability. This kind of systems fluctuates between near-field and collective surface modes, and these collective modes are associated with narrow peaks. They give extended time response, and we observe enhancement of the electric field over large areas. So these kind of systems could be suitable for applications as perfect absorbers surface enhanced spectroscopies, as Javier will show you in the next talk, and plasmonic sensors. Thank you for your attention.
Okay, thank you, Amilcar. Well, we have time for one quick question, if there is any. Any questions in the audience? I will wait a bit because before I realized there was a question in the chat and it takes time until. No, no questions. Well, you still have time until the next talk because this is part of the same group. So you can still ask the questions in the chat and can be answered publicly so that we can all enjoy. So if there are no questions, since the time was already up, then I would move on to the next speaker. Thanks again, Amilcar, for this very nice talk. And the next speaker would be Javier Rodríguez Alvarez from the University of Barcelona, who will be talking about SERS in arrays of geometrically frustrated plasmonic nanoelements.
Okay. Please, Arantxa, let me know if you are able to see my shared screen. Can you all see it?
Yes, perfect.
Okay. So, okay. So thank you all for attending to this presentation. My name is Javier Rodríguez Alvarez, and I'm a PhD student in the Magnetic Nanomaterial Group at the University of Barcelona. And today I would like to talk to you about SERS in geometrically frustrated plasmonic nanoelements, in arrays of geometrically frustrated plasmonic nanoelements. And this is kind of a following up of Professor Amilcar Labarta's talk. But I would like to center my speech around some specific applications. And in this case, the use of this kind of structure for SERS. So I'm not going to go into details in which is Raman and what is SERS, because it has been wonderfully explained by before. But let's just refresh some basic statements. And some of these is that SERS basically stands for Surface Enhanced Raman Spectroscopy. And thus, speaking about Raman is something that we should always do at the beginning of these presentations. So we just have to know that Raman scattering is an inelastic scattering. This means that the incident radiation and the scattered radiation do not have the same energy. And this energy, it's invested, it's used to excite some vibrational, rotational, and other low frequency modes. And thus, by taking a look at the spectrum of the scattered radiation, at least comparing it with the incoming radiation, we can see that for each analyte, we can get a particular collection of peaks. So this is something very good because it allows us to know the structural and unique fingerprint for each analyte that we can think of. But this has a problem, that this signal is very, very weak. These processes are highly inefficient. So we need to find something to enhance this intensity of the signal. Well, and the answer to this problem is SERS. SERS is nothing more than taking this analyte and placing it on top of a nanostructure surface. And by exciting this analyte with the same Raman setup, we are also exciting the structure. And the structure has a complex interplay with this analyte. But in the end, what we should know is that we are able to increase the Raman scattering signal by many orders of magnitude. So how are we doing these structures and how are them? So they work pretty well for SERS. Well, we just take a silicon wafer and we deposit several layers on top of it, which is, which is just a continuous gold layer. On top of that, say a continuous silicon oxide layer, and then a resist on top of all this setup. This resist will be used in the process of fabrication through electron beam lithography. And by using an electron beam, we're going to draw the design pattern on that resist, and then that pattern will be etched So the only thing that will be left is evaporating a thin film of gold on top of the system. And by a final step, which is called liftoff, we are going to get rid of the excess resist all along with this fine layer of gold that in principle we are not interested in. So we can design patterns like this. This is an SEM image of these systems before liftoff, and this is after the liftoff, when you can see that here you have the extra gold layer on top and here you don't, and you end up having something like this. So with the electron beam lithography, we can get to easily control fine parameters of the system. As you can see here, we can craft asterisks of many shapes and distance between them, even reaching to gaps between the structures, like Professor Amir Carlabartas introduced, of tens of nanometers, which is something very convenient for our case. So if we compare our structures with commercially standard substrate for Raman, we can see that this is the performance of a granular silver substrate, where we are here just taking a drop of a solution where we have our analyte at a concentration of 10 to the minus 3 molar, and placing it on top of this granular silver and waiting for the drop to dry. Then we perform the Raman spectrum and we get this nice characteristic collection of peaks. But if we repeat this very same experiment, but using one of our substrates, we can see that we get the same collection of peaks, but in general, all the intensity of the peaks is better. And we even get high enhancement of peaks that before were barely visible. So this is good news for the performance of our structures. But we can go a little bit further and try casting drops of a smaller concentration, in this case, a 10 to the minus 6. And we are using another molecule. This is crystal violet, which you have already seen as well. And you can see that if we use the substrates with the liftoff process and without the liftoff process, we get really different results. We really discovered here that the samples without the liftoff, so with this extra gold layer on top of them, which this will be a continuous gold layer with asterisk-shaped holes on that layer, give us a much better performance of these substrates, because we have seen the same peaks, but we can see them clearly. And this is something that at first surprised us, but we wanted to go a little bit deeper on that. So we chose another pattern, another design. Sorry, but before that, we can go to the final test of these kind of structures, again with the asterisk, and we were able to detect even a single monolayer of, in this case, of mercaptopyridine. This is just a functionalization of the surface of the substrate with a monolayer of this molecule. Here you can see an SIM image of this, of the top of these structures, and you can even get to detect the same peaks. So as I was saying, if you take another design, for instance, this honeycomb lattice that you have already been introduced to, you see again the same results, with the difference that this time the drop that was casted was of a concentration of 10 to the minus 9 molar, which was something very remarkable for us, because this is again a very simple experiment to conduct, because it's just taking a drop of the desired and of the solution that we are analyzing and casting on top of the surface, waiting for 2-3 minutes for it to dry, and then performing the Raman spectrum. So after seeing all these results, we were very curious and we wanted to go deeper in the reasons why these samples without the liftoff seem to systematically outperform their companions with the liftoff process performed successfully. So in order to gain further information on what was going on here, we took advantage of some additional optical measurements and numerical simulations performed in this last structure that I presented to you. So here what you're seeing is the experimental measurements of the absorption of this structure. We got the absorption spectrum and the simulation performed for the very same structure. And you can see that already the results are in a fairly good agreement. We can see excitations are around the same wavelengths. And what is more important is that if you take a look at this part of the spectrum, precisely at the wavelength of 785 nanometers, which is the exciting wavelength for the Raman setup, you can see that this structure already shows a strong interaction with this wavelength, because with this wavelength will be around here, and you can see that the absorption peak is in the vicinity of this wavelength. So we can already tell that this structure it's interacting strongly with the Raman laser in some way, which is enabling for this enhanced Raman response. So after this first approach to studying the structures without the liftoff, we wanted to go further, and then we decided to take a look at the near field of the structure, this time only by simulation means. In order to do so, we decided to remove this continuous gold layer here, which was acting merely as a mirror. And before doing that, we checked and we saw that the simulations with and without this gold layer did not affect the number of peaks that the spectrum was showing, and didn't affect that much to their location. So we concluded that the effect of this gold layer was something of a second order of importance, let's say, and removing this layer made all the interpretation of the results much simpler. So if we take the same system again, but without the gold layer, we are left with the honeycomb structure on top of these trenches, which will be the darker part in this SEM image, and the same honeycomb structure on top, but this time in a negative way, such that we have a continuous gold layer with hexagonal honeycomb pattern curved in it. So if we take a look at the absorption of this structure without the mirror, we can identify quickly 4 absorption peaks, which could be related to these 4 absorption peaks that you can see here in the simulations. So in principle, the excitations of the lattice were at least very, very similar. So if we take a look at the excitation of the near field in these structures, we get something like this. Before going into detail of these maps, you should know that what you're seeing here is it's a distribution of electric field. The redder the color, the higher the electric field intensity. And we wanted to probe 3 different planes of this structure, always by simulation, I insist, which these 3 planes were the positive honeycomb structure, what you can see here. It stands for this image here. The negative honeycomb structure, where everything is gold and you have air in these trenches that you can see here. So the field is consistent with this distribution. It's mainly concentrated in the trenches. And we also wanted to see what was happening right above the structure, because in the end, if we want to functionalize this structure with a molecule that we want to detect, those molecules are going to be sitting mainly on this plane here. So this number 3 is the electric field distribution 20 nanometers above of the structure. So first of all, if we take a look at the peak that is of the most interest for the Raman, for the cells, we can already see something very interesting. Here, what you're seeing, as Milkar said before me, is a collective excitation of the system. Why? Because you can see a pattern that is not following the position of the elements, but it's following the symmetry of the lattice. So, and what is more important, sorry, you have this pattern outside of the structure. So that is this electric field distribution, this collective excitation, it's able to probe the molecules that would be sitting on top of the structure. So for the sake of completeness, if we take a look at the near field at other peaks, we can see a wide range of interactions, sorry. But all of them are of a more localized nature. All of them except for this one. So we can see, which is again collective, sorry. So we can see that we have 2 collective excitations of this structure, one at 760 nanometers, and the other one at 1030 nanometers. Unfortunately, this collective excitation it's not of any use for the Raman or sensing purposes, since this collective excitation is concentrated in the electric field in the bottom structure, and this electric field distribution is happening inside of the silicon oxide. So it's not accessible for a molecule of the outside. So now you may wonder, why do we precisely have these collective oscillations on this collective excitation, only in these two wavelengths, and only in the top structure for the 760 nanometers, and only on the bottom structure for the 1030 nanometers? Well, it may be clearer if we take a look at this explanation. If we consider the parameters of the structure, we can see that this honeycomb structure had a pitch of 866 nanometers. So if we remember the diffraction condition for a lattice, we can write it down to be something like this. Okay, which is something like this, where we have introduced effective refractive index here to take into account the fact that the bottom structure is embedded in silicon oxide and the top structure is mainly in contact with air. So if we put the numbers here and we take the effective refractive index as 1 for the top structure and the effective refractive index as 1.4 for the bottom structure, we get exactly the wavelengths that we are in which we are seeing the collective excitations. And which is more interesting, we are getting that the diffraction condition is fulfilled for the top structure at the wavelength at which we have the collective excitation of the top structure, and we get the same result for the bottom structure at which the wavelength at which we would expect that for the bottom structure. So finally, just to wrap everything up, we have seen that SERS is a useful technique to detect biomolecules in really low concentration, and even by simple methods. We have also shown that the plasmonic structures presented here have clear advantages over standard SERS substrate, and more specifically, those structures without the liftoff are outperforming the structures with the liftoff. And finally, the excitation modes that are responsible for this high enhancement of the electric field in the surface of the structure are due to collective excitations of the system. So this connects with what we were looking for and what Amilcar was explaining before. And we can also add that these collective excitations are strongly related with diffraction conditions of each structure. Well, thank you for your attention, and thank you also to the to the NanoNEMS group at Autonomous University of Barcelona for the use of the clean room environment, and of course Dr. Ana Conde for her amazing work starting all these projects. Thank you very much.
Thank you very much, Javier. Very nice talk. Time is open now for questions. We have about 3-4 minutes for questions. Anybody wants to start? Everything is very clear, or okay, then maybe well, I can ask a question just to break the ice. So you've shown results on honeycombs. Have you done a work on other type of lattices? These Kagome lattices seem to be quite interesting from the previous talk. Do you have something to say about those lattices in the way they perform, especially for these SERS sensing applications? What are your thoughts?
Yes, sorry, we're still working on these Kagome lattices. It's a lot of work to be done yet, but I didn't want to present this kind of lattices in this presentation because we mainly haven't been able to fabricate them yet due to all this coronavirus lockdown thing. But we, based on the simulation, some of them shown by Amilcar and some of them that are still being analyzed by us, we really expect these Kagome lattices to have a lot of things to say about well, the enhancement of this electric field, and maybe to shifting towards other applications, because here we have mainly showed the results for the systems that exhibit no transmission, and well, basically we were working with reflection, but we have lately seen that this combination of two lattices, this stacking, may lead to interesting interactions between this positive and negative structure, or maybe two identical structures. And so taking into account the transmission may be something that will involve for sure the Kagome lattices in some way, because in the end it's all about geometric frustration, and these lattices are the best ones in this.
Okay, thank you. I see one question in the chat from Clara Bujalans. I'm not sure it's pronounced this way, sorry. Very, very nice talk. She says, what is the angle of incidence that you use when illuminating the gold honeycombs?
That's a good question. We have only performed simulations as well as experimental measurements at perpendicular incidence. So we are working with normal incidence to the structure. So we would need to think about what would happen with a different angle of incidence, but it's something that we can. I mean, it's something that we for sure want to check out, because by now we have been busy understanding how the structure works. But yeah, it's something that for sure I hope that I will be able to tell you anytime soon.
Okay, thank you. Okay, of course, thank you very much. Then she answers. Maria Ujue Gonzalez, our previous speaker, has a question. Interesting talk, thank you. Would the system work similarly with a honeycomb gold structure on top, but empty holes? No gold in the holes?
I'm not sure I'm understanding your questions. You mean, Maria Ujue?
Means that in the trenches, then you don't really have gold, so that only with the top.
Okay, now I see.
Well, if not, Maria Ujue, you can, I think you can open the mic if you need to clarify.
Yes. Yes, it's exactly that I was meaning. Instead of being like a no lift off thing, on purpose you were putting just the gold on top, but you were not having the gold that fails in the holes.
Only having like a continuous layer with trenches
Exactly.
in a way. We have performed some simulations on that, and that structure also gives a response. You also get nice peaks when looking at the absorption spectrum, but they are not so interesting because they are not so narrow and they are not so intense. So everything seems to indicate that the interplay between these two structures plays an important role, despite the fact that the excitations of the collective modes in the top and in the bottom structure seem to be kind of independent. For sure, there's some kind of averagization between them, or at least they can see each other for sure, because the results is what are telling us.
Thank you very much. Interesting.
Okay, thank you very much, Javier, once more. And now we move on to the next speaker. We have an invited speaker again. She's Angela Demetriadou from the University of Birmingham in the UK. And she's going to talk about excitations and radiative properties of plasmonic nanoantennas. Welcome, Angela, and whenever you are ready.
Okay, sorry. Can you hear me now?
Yes.
Can you see my screen?
And now we see the presentation, yes.
Yeah, sorry, I have some problems with the, cannot see everything. Hold on.
We don't see the screen again.
Hold on.
We saw it briefly.
Okay, it should work now, right?
Perfect, thank you.
Okay, yeah, sorry, I just had the participants window open and it was covering half of my screen. All right, okay, thank you very much for the introduction. I would like to thank the organizers for the invitation. My name is Angela Dimitriadou and I'm based in the University of Birmingham. My talk is a little bit different than the rest of the talks. It's a theoretical talk that I will be talking about theoretical work. And mainly I will be focusing on what's happening in the hotspots that all of you have mentioned before. And hopefully I'll give you a bit more insight on a bit more details on what's happening in those hotspots that hopefully you can utilize in your work later on. All right, okay, so the title of the presentation is Excitation and Radiative Properties in Plasmonic Nanoantennas and Plasmonic Nanocavities. I will start the talk by explaining what do I mean by plasmonic nanocavities and the systems that I'm focusing that I'm investigating. Briefly mention how to use suppressed quenching in such systems, and then highlight some peculiar behavior that we have seen 2-3 years ago in such plasmonic antennas. And then I'll introduce some theory on how do you better understand what's going on in those systems, and then some new results at the end on what's happening. You have the near field, the hotspot, and how does that emit into the far field, and what do you see in the far field? Okay, so when I refer to plasmonic nanoantennas and plasmonic nanocavities, all the systems that I'm dealing with, I'm talking about plasmonic gaps that are only 1 or 2 nanometers in width, or height, sorry, the height of the plasmonic nanogap. These are extreme cavities, are very, very small gaps, and recently in 2000, I think 14, 15, that they were first fabricated, and the way that experimentalists fabricate them, mostly they have what I'm showing here on the left. You have a flat surface of gold. You assemble a molecular monolayer on top of it, where the molecule that you choose, it defines the height of your gap here, and then on top of the molecular monolayer, you assemble a gold nanoparticle, and you form this very well controlled gap here. This is the main method that the experimental group that I'm collaborating with, they use. There are other groups that they use other techniques like DNA origami, which gives you even a greater control on the size of the gap that you have. However, it's more difficult to go down to 1 or 2 nanometers. It's usually around 4 or 5 nanometers with the DNA origami. Why would anyone need such extreme gaps? Why would you need such small plasmonic cavities? Well, by having such a small gap, you confine your fields, the hotspot that you're creating, it's a lot stronger. You confine even higher order modes, that it's a lot more difficult to confine them if you have a gap of 5 nanometers or 10 nanometers. And by confining those higher order modes, they start becoming radiative. So instead of being dark and absorbing energy, they actually emit to the far field. And a reason that we also highlighted 3-4 years ago is that with these cavities, you can suppress quenching. And I'll talk a little bit about that. And here is one example on what you can do with such extreme plasmonic cavities. That was work from 2016, it's 4 years ago. If you place a photoluminescent a molecule within these cavities, it's this molecule here that is standing up, this is methylene blue. Because the fields are so extreme in this cavity, what you see a strong coupling at room temperature, even with a single methylene blue molecule. And here is the experimental results from Jeremy Bomber's group, where if you sample, you have the same system with the methylene blue parallel, so basically it's not aligned with the field enhancement in the gap, you only see the plasmon, so these are scattering cross sections. If you don't have the methylene blue within this system, you again see only the plasmon emitting to the far field. But once you have the combined system where the methylene blue is inside this host molecule, where it allows it to stand up and be aligned with the field enhancement in the gap, you start seeing the two hybrid modes. Basically, your plasmon mode, the one peak splits and it becomes two, where it's a clear indication of the strong coupling between light and matter, in this case, the plasmon and the methylene blue molecule. And this is quite significant because it allows us to investigate matter down to its most basic element. And the reason that you can see strong coupling at room temperature with a single molecule is because, as I said before, you can suppress quenching. First of all, what is quenching? When you have an isolated plasmonic structure like a spherical nanoparticle and you put a quantum emitter close to it and you measure the emission rate, which is, I'm showing the formula here, what you see is that as I move this quantum emitter closer and closer to the surface of the spherical nanoparticle, you see the emission rate increasing. But up around 10 nanometers, when I'm about 10 nanometers away from the surface, you see a depletion of the emission rate. And the reason for that is because, well, we usually say that these kind of structures, they have the dipole mode, and that's the one that we usually consider and ignore all the higher order modes. And the reason that we do that is because that's the main mode that radiates to the far field. That's the one that we efficiently excite to, and that's the one that we we see in the far field, we measure in the far field. However, there are higher order modes supported by this system, and that there are more, the field profiles are more confined on the surface of the nanoparticle. So as I move the emitter closer and closer to the surface of the nanoparticle, I couple energy to them. And these modes, the second order mode and all the higher order modes, are dark. So as I move closer and closer to the nanoparticle, I channel energy into dark modes, and that's why my emission rate reduces. Now, if I do the same test, numerical experiment, if you want, for the this system that we call the nanoparticle or mirror system, then what you see is that the emission rate keeps increasing and exponentially, and you never really see it reducing. And note here the difference on the scale on the emission rate. And the reason for that is because you're confining this mode from the nanoparticle into the gap here. And if I'm standing very far away, where I'm detecting the emission from this system, this mode and this mode, they don't look too different. So basically, this mode now, it is allowed to emit to the far field. And because this acquires a radiative part, the energy that I couple to it, it doesn't get lost into ohmic losses completely, but part of it is radiated to the far field. And that's why I'm allowed to increase my emission rate that significantly, even if I'm just 1 nanometer or half a nanometer close to the surface of the nanoparticle. When we were doing that work, we also measured the excitation rate of a quantum emitter in these two systems, which is the red line here, the dashed one for the isolated nanoparticle, and the full red line for the nanoparticle or mirror, and the radiative decay rate, which is plotted in blue. What we've seen for the isolated nanoparticle is that the excitation rate and the radiative decay rate, they were almost degenerate. There is a small difference to them, but they're almost degenerate. However, for the nanoparticle or mirror, they were different, quite different in value. And we couldn't quite understand why that was happening. Just to give you a bit of an insight, when I'm saying excitation rate, what do I mean? I mean that I have a plane wave incident on my system, and I'm measuring where I'm planning to put the quantum emitter. I'm measuring the field enhancement, because that's how strongly my quantum emitter will be excited. While the radiative decay rate, what I'm doing, I'm putting a quantum emitter, a dipole, and when it emits a photon, I'm detecting into the far field how much of that energy from the quantum emitter reaches the far field. So it makes sense that for the isolated nanoparticle, the excitation rate and the radiative decay will be the same because of reciprocity, but I would expect something similar to happen for the nanoparticle mirror, but it does not. We started looking at other similar designs. For example, moving into a plasmonic nano antenna, this is the dimer antenna, took the same nanoparticle as before, What I'm plotting here is the spectral behavior of the excitation radiative decay rate. Again, you see for the full spectra, for the isolated nanoparticle, it is almost degenerate. And the same thing happens for the dimer antenna. So it remains degenerate. However, it is different for this particular system here, well, for the nanoparticle or mirror system, where you see the radiative decay rate is about 3 to 4 times stronger than the excitation rate. That means that this system here radiates to the far field a lot more efficiently than I can actually couple energy to it and couple energy into my quantum emitter. So because we want to look at how a system emits to the far field, I cannot really take a quasi-static approach into this problem. I need to have a wave vector within my equations in order to be able to model it properly. And so we used me theory, and here I will just introduce a little bit terminology that I'm using later on. People familiar with me theory probably will find this very boring. It's just for people that are not too familiar with it. So what I need to do, I need to solve my Helmholtz equation, then homogeneous differential equation that I'm showing here. And the best way to do that is by obtaining my Green's d-adic, which is basically a generalized solution of this equation there. And then from that, I can construct back my electric field by having a dot product between my Green's d-adic and the dipole moment of my emitter at that position there. The way to do that, the way to solve this in homogeneous equation, you first solve the homogeneous equation, which in this case, they look like this, and I end up with 3 eigenvalues, which are Lm, zeta, and 2 eigenvectors, the m and n. There is one more which is ignored here. The L and m eigenvalues are discrete. The zeta eigenvalue is continuous because it represents my wave vector, and because I'm coupling into the far field, these are continuous and they're not discretized. And the way to write down your Green's d-adic is basically you need to sum up over all your eigenvalues, so that n there is L, m, and z and zeta, and add up all the eigenvectors or the solutions of that system. And once you do that, you end up with an equation that looks like this, which might be a bit complicated and looks a bit confusing. But if I get my electric field by applying this here, what I end up with this equation here. So I'm basically multiplying the Green's d-adic with the dipole vector that it has the polarization, the dipole moment of my emitter, and I end up with this equation here, which may look quite complicated, but if you look carefully, this dipole moment, it actually only operates on the eigenvectors that are dependent on R dash, which is the position where I put my dipole. So you end up here with a scalar term. So this is a vector, this is a vector, and you end up here with a scalar term or an incoupling coefficient, if you want, that measures how much energy my source placed at this particular position couples into my modes. So the blue part here and this one measured how efficiently I couple energy into my modes from a source being at a particular position. Now, this part of the equation describes the electric modes, and this part of the equation describes the magnetic modes. If I'm looking at a plasmonic system, a metallic nanoparticle, the magnetic modes are 2-3 orders of magnitude smaller than the electric ones. So I'm basically looking at the electric modes, so this part of the equation only. So yeah, this is the same equation as before. I put it here so you can have a look. And if I want to write down the scatter fields coming from the same system, what I write down is a very similar equation. The only difference is these coefficients here that they're in purple. And these are my scattering coefficients, and these are dependent on the material that my nanoparticle is made of and its radius, its size. And these are the standard me theory scattering coefficient. To obtain the radiative decay rate, so how much of the energy that this dipole couples into my plasmonic modes and how efficiently those plasmonic modes emit into the far field, I need to do some further algebraic mathematical derivations, solve some integrals, but in a nutshell, you end up with a formula that looks like this. And again, these are my electric modes, these are the magnetic modes. The blue describes how efficiently I couple into the modes by having the dipole at a particular position. The coefficients here, they describe how efficiently the plasmon modes emit to the far field. And these extra terms there is how efficiently the dipole source couples energy into free space. So basically, I have this dipole emitting. If there was nothing there, there was no nanoparticle, then these terms will go to 0. And then you will just end up with the purple terms, the dark purple terms, and nothing else. And basically, you end up with a radiative decay rate, which is 1. And from me theory, and this is taken from Bochren's book, you end up, the scattering coefficients can give you the normal modes of the system. And the first 3 electric ones, so in our case, the plasmonic ones, they look like this. And they are quite relevant to the spherical harmonics, the profiles of the spherical harmonics. So I plotted them here. This is just some pictures that are of the spherical harmonics that I took over the internet. And you can see that basically that each pole of the spherical harmonics gives you the pole of your me mode, the plasmonic mode within the spherical nanoparticle. So you've got a plus minus, you've got a plus minus, and so on. And there are quite a few more modes later on. However, here I'm dealing, what I want to study is not an isolated spherical nanoparticle. I want to look at a dimer antenna. And here I have the, what you can do, you can write down the scatter fields from this system here with the 2 spherical nanoparticles in a similar form as before. So you basically are expanding it into the same set of modes. The only difference is that these scattering coefficients now, instead of being only dependent on L, they're also dependent on M because you have different emissions directions. You're losing the spherical symmetry that you had before. But the meaning of the equations remain the same. And to obtain these scattering coefficients, you can do it 2 ways. You can apply your boundary conditions and obtain them, but that's pretty difficult because the system explodes here in the gap. You have too many wave functions there. Another way is you can calculate them numerically and then fit them here in this term, in this formula, which will allow you to find what's the scattering coefficient for a given L and M. And you can do a similar thing for the other scattering coefficient. So going back to the radiative decay rate formula that we had before, you can plot the full result, which is the blue dashed line here, and the black one is numerical results. And you see this is for a very, very large spherical nanoparticle. It's a radius of 500 nanometers. And you start seeing the modes of each, the separate modes from each multiple. But I'm really interested to see what's going on here in the optical regime. And if I zoom in there and decompose my modes, which this methodology allows me to do easily, then you can start seeing that that green line, that's the 3rd order mode. This is the 4th, 5th, 6th, and 7th. So what do you see? You see all the higher order modes excited. These are very large nanoparticles, so you see, well, all the higher order modes radiating efficiently to the far field. So before I was comparing the radiative decay rate and the excitation rate, and I was seeing differences. So in order to calculate the excitation rate from this methodology, what I have to do is just take my dipole that I had here in blue and take it to the far field. So make R dash go to infinity. And once you do that, then your formula simplifies to this. And you also have a selection of the M modes that, this becomes 0 unless M is equal to 1, which is if you have an X polarized plane wave. If you have a different polarization, that M becomes something else. And the excitation rate is basically taking this field plus the incident one and normalizing it with the incident field and along the polarization of where you put your emitter next to the nanoparticle. And if I plot the same thing for the excitation rate now, I see that the excitation, the full result with all my modes, there is the black line here. Now for the same nanoparticle, 500 nanoparticle in radius. And if I decompose my modes, this is the first order mode, this is the third, this is the fifth, and this is the seventh. And I immediately see that I'm missing all the even modes from this system. The plane wave, I have a plane wave incident onto the spherical nanoparticle, very large spherical nanoparticle. What I see is that I'm actually missing all the odd L modes that cannot couple into my emitter and they cannot excite it. And that's where the difference is coming, is the difference that you don't only see for the nanoparticle mirror system, it's actually something that you also see for very, very large spherical nanoparticles. And here I'm plotting both the radiative decay rate and the excitation rate. So in the red is the radiative decay rate, and blue is the excitation rate. And you clearly see that here you have the second order mode where you have a strong radiative decay rate, while the excitation rate, you just have the value and there is no peak. Okay, why does that happen though? Why do you see that difference? So I said before that for the excitation rate, you send a plane wave and you measure the excitation at the position where you want to put your quantum emitter, your molecule, your fluorescent molecule, your molecule you want to do search on. So here I'm choosing an Y polarized plane wave and a specific wave vector incident on the structure. And by choosing an Y polarized plane wave, what I'm basically choosing is the M equals -1 in this case. So this is a set of the spherical vector harmonics, or the set of the spherical vector harmonics. And by choosing this polarization incident onto a spherical nanoparticle, I'm basically choosing only these ones. I'm doing a selection on which spherical harmonics I'm picking because of my polarization and the wave vector direction. And you can immediately see that, well, I'm sending this polarization, I'm gonna have a plasma, the dipole resonance oscillating like this, which is basically the first order mode here. This one here, you're gonna have a plus, minus, which is what this one is showing. But if I put my dipole at this position here, it means that you're gonna see a 0. You will never be able to couple energy to that emitter from this particular mode. However, for the third order mode, you're going to have a maximum, and so on. It goes on like that for the higher order spherical harmonics. And this is the reason that the second, the even modes do not show anything in the excitation rate. So yeah, that's placing the dipole there oriented along my incident polarization where the maximum excitation should occur. Okay, and this is something that you observe only if you're beyond the quasi-static limit. If you're looking at systems that they have non-quasi-static elements. And here what I'm plotting is in the x-axis is a wavelength, and in the y-axis is the nanoparticle radius. So down here, I'm just on the limit of the quasi-static limit. And you see there is some resemblance between the radiative decay rate on the left and the excitation rate on the right. As I make my nanoparticle larger and larger and larger, you see that for the radiative decay rate, I have the first order mode, the second order mode, the third order mode, fourth, and so on. However, for the excitation rate, I'm missing all the even modes. So this is something universal that you see for all non-quasi-static metallic structures. And it happens because of the electric field polarization, and the wave vector that you're choosing, it selects basically the modes that you're excited. So what I want to see a coupled system. I want to see a plasmonic nano antenna. I want to see the nanoparticle or mirror what's happening in those systems. I don't want to see an isolated nanoparticle. But what I'm going to do here is I'm going to assume that the spherical nanoparticle, the mirror in my nanoparticle or mirror is a very, very large spherical nanoparticle. So I start with a very, very large spherical nanoparticle, which supports a certain set of discrete modes, right? The first order, the first mode is basically the degeneracy of 3 modes, which is these 3 modes here. The second order mode is a degeneracy of 5 order modes. And the reason that you have the degeneracy, you have a spherical symmetry on your nanoparticle. And the same, and continue so on for the higher order mode. So for L equals 3, the third order mode, you have 7 modes degenerate. And for the L equals 4, you have 9 and so on, it goes on. And if I have a very small nanoparticle of a radius of 40 nanometers, you see a very similar behavior. Again, you see for the first order mode, 3 modes that are degenerate with each other, which correspond to these 3 spherical harmonics. The second is the 5 modes, which correspond to these 5 spherical harmonics, and L equals 3, you have 7 degeneracy and so on. Now, if I want to look at the nanoparticle or mirror, what I can do is I can couple this very small nanoparticle with this very large nanoparticle, and I have an approximate nanoparticle or mirror system. And the way that I structured the modes here for the 2 systems is I put them where they should be energetically, so on this axis here. So my first order mode for the very small nanoparticle is aligned with the higher order modes of the very large nanoparticle. So when I add the 2 together and bring them together, what you start seeing is you mainly see enhanced the modes of the very small nanoparticle, but you start losing the degeneracies of your modes. And the reason for that is you're breaking the symmetry of the system. So you do not have just a simple spherical nanoparticle. By bringing this one next to it, you're breaking the symmetry that you had before in the nanoparticle. And what I'm doing here, I'm plotting the field enhancement in the gap of these 2 modes and also putting them energetically where they should be. So the 1,0 mode, which is shown here, you just see a maximum here in the gap, which is the mode that we usually see and consider in systems like that, and we ignore everything else. There is though another mode, the 1,1 mode or the 1-1 mode, which looks like this. It has a 0 in the middle, and then it has a plus and a minus on each side. Sorry, okay. And then the second order mode also splits its degeneracies. You have the 2,0 occurring at lower energies, and then the 2,1 are slightly higher, and the 2,2 are slightly higher energies. And here is how they look in the gap. So you have the 2,0 mode there, which has a plus, a 0, and then a minus. And then you have the 2,1,0, which is basically the second order of this one. And then you have the 2,2 mode. And if you look carefully, they actually correspond to the modes that the profiles that you see for the spherical harmonics in this case here, which are disturbed a little bit by the very large nanoparticle. And so on, it keeps going on for the higher order modes. They all split their degeneracies. And here I'm plotting for the third order modes, where you have the 3,0, 3,1, 3,2 is the second order of this one. And then you have the 3,3 mode. And they're all confined in the gap because of the strong coupling, because of the tight coupling between the 2 systems here. And now if I want to see what's happening to the excitation and radiative decay rate in this system, I start by plotting both quantities for the nanoparticle, the small and the very large nanoparticle, when they're separated, when they have a very large separation, in this case 50 nanometers. With 50 nanometers, it means they're not really interacting with each other. And because the larger nanoparticle gives you a stronger behavior, the only thing that I'm seeing basically in this figure is the behavior coming directly from the very large nanoparticle. So I see the difference between the radiative decay rate in red and the excitation rate in blue. I see the differences because of the even modes not being excited from for the excitation rate. This line here, the dashed line, shows where this mode here is for the small nanoparticle. So as I start bringing the small nanoparticle closer and closer to the larger one, so this is a gap of 20 nanometers and a gap of 5 nanometers, what I'm saying is that the same difference remains in between the radiative and the excitation rate, but I also see that these modes here that I had before, they don't actually reduce in intensity. What you're seeing is that you have a field enhancement much stronger within this region because of the coupling of the two systems. So I'm basically enhancing this mode, and you end up not being able to see these modes because they're weaker. So you see the scale difference on the order of magnitudes here. So this part becomes about 5 orders of magnitude stronger than this one. This still exists, it's still somewhere here, but it's so small that I cannot really see it in this system. So basically I do have other modes here. It's not only one mode as we thought initially, there are a lot of others. It's just these are the dominant ones. And the behavior between the radiative and the excitation rate remains the difference between them for the same reasons as you had them there for the very, very large nanoparticle. It's because there are modes that you're selectively not exciting with a plane wave. And the same thing happens for the nanoparticle or mirror. So again, this is the radiative decay rate and the excitation rate in blue. The difference between the nanoparticle or mirror and this system here is that now my higher order modes here for the very large nanoparticle, when they were discrete for the very large nanoparticle, for the sphere, they just become continuous. And it is what people refer to as the propagating SPPs, but the same selection of modes and polarization with the incident polarization remains within the system. So what I would like to talk briefly afterwards is how does each of these modes that they exist within this very small gap, how do they emit to the far field? What's the profile of the far field emission? So here I have again is the same set of modes that I introduced before, sitting on an energy axis here, and the lowest order mode, which is the one that we usually consider, which is the 1,0 mode, emits in a conical way. So you see basically a donut in the far field. If you were measuring in the far field around the structure, what you would see emission. This is around 60 degrees. Experimentally, I think it's around 55 degrees. So that's not too far off. For the 1,1, so it emits conically like this, sorry, yeah. The 1,1 mode though, it emits vertically up. And I have an arrow here showing that it emits vertically up. The 2,0 mode emits similarly as the 1,0 mode, and the 2,1 mode emits similarly as the 1,1 mode. The 2,2 mode emits at the same angle more or less as the cone of the 2,0 mode and the 1,0 mode. However, it has 4 lobes, which correspond to the 4 lobes that you have into the near field here in the gap. So if I place a dipole in my gap, and it's not exactly, if it's exactly in the center, basically because all these modes are 0 in the center, then it won't really couple efficiently to all these modes. It will only couple into these ones. So if I put it exactly in the center, it will emit in a conical way. However, if it's a bit off center, so here I'm showing if it's about 5 nanometers off center, what you start seeing an emission that is a combination of this, basically, and a little bit of that one. If I place my emitter even more offset, like 10 nanometers, you see a different profile into the far field. And this is something that was seen even experimentally. I should have cited the paper here. The last few months published in PNAS. Sorry, I should have cited the paper. Quickly, I would like to say that spherical nanoparticles in reality are not really spherical, are very, very rough structures. They have different crystal lines, and they're actually here. This is a collection of SEM pictures of the same nanoparticle, and you see that it is basically a polygon. And what experimentalists can do, you can shine a laser and immobilizes the gold atoms, and you can even control the size of the polygons that is opposite to the mirror here. And when we were doing those calculations and those experiments, we were observing very peculiar behavior. That this is the scattering cross section, and what we would see is that as this will get larger and larger, you start seeing higher order modes emitting very efficiently, while lower order modes will become dark, which is something very unexpected. And at the time, we were thinking that you start having these modes switching off while the second order modes are switching on. Somehow something is going on there. And what we realized after doing this analysis of the higher order modes in the system is that as you create a facet in the system on the small nanoparticle here, what you're doing is you're shifting energetically your modes. So the first two modes for this particular facet size that I picked here, which is I think is 20 nanometers, you see these two modes moving energetically a little bit lower, but they keep their order. However, for the second order mode, you see this mode here, which used to be up there, being lower energetically. And for the third mode, you see something like that, fourth and fifth, so on. And all these modes, higher order modes, are dark, very, very, very dark. So what they're doing, they start interfering with the emission of these modes, which are my bright modes. And that's why you start seeing this behavior in systems when you start changing the facet size. So you end up mixing the frequency where these modes are up here. And finally, we just recently started looking at more complicated nanoparticles. This is a Rumbock tetrahedron that I'm showing here. And what I highlighted there is the facet that is actually parallel to the mirror as we assemble it parallel to the mirror. And you see a very similar set of modes, even though you're actually breaking even more the symmetry on your nanoparticle. You see a very similar set of modes, which we managed to classify, well, most of them. And what you see is the breaking of symmetries between the degeneracy, the breaking of the degeneracy between your modes. So this mode here is this one here, the 1, 0, and this one here that sits energetically at lower frequencies is this and this mode. And for this particular facet, assembled opposite to the mirror, this and this mode are degenerate. And the reason that they keep their degeneracy is because if you look around this facet, you still have a symmetry on this plane and that plane there. So you have 4 square facets surrounding this square facet itself. So there is some symmetry remaining in this system. However, if I pick this facet to assemble it opposite to the mirror, I'm breaking that symmetry. And again, this is a very similar mode as to what we had before. And I'm breaking that symmetry, so this and that mode are not degenerate anymore. So it depends a lot on what's the neighboring facet around the one I'm assembling opposite to the mirror, because of the electrons getting scattered from the edges of the facets as they travel on the surface of the nanoparticle. So they will have a different path on this direction than on the other direction. So to conclude, when you have non-quasi-static elements in a plasmonic nanoantenna in a plasmonic system, then you start seeing that it can radiate to the far field a lot more efficiently than you can couple energy into the system, into a quantum emitter that exists into the system. Also, if you're going into very small gaps of just few nanometers, it is important that you do not ignore higher order modes. Such systems, they support a very large set of modes that they're not insignificant, and they start actually affecting what you observed into the far field, what you measure experimentally, and they change actually the emission. How do you emit to the far field? And as you break symmetries within your system, you have a faster nanoparticle or a polygon or whatever, then you start breaking the degeneracies and the behavior of what we initially had for a very ideal spherical nanoparticle. Quickly, the people that did the work is Colin Bedingfield. He's a PhD student in my group, and Dawood, he was a PhD student who graduated last year. He's in Thailand now, working in a company on quantum technologies. And the people that pay the bills is the Royal Society and EPS-RC. So thank you for your attention.
Thank you very much, Angela, for this very nice talk. And well, there is only time for one very urgent question. So I see one in the chat, so I will read it to you. Let me see. This is, from Jose Angel Sanchez Gil. Nice talk, Angela, very insightful. One question for the nanoparticles on a plane. When explaining the out-of-coupling efficiency of the dipole in the gap, you connect it to the mode profile. Does it correspond to the LDOs in the gap plane?
The local density of states.
The local density of states, yes, in the gap plane.
The local I think you're referring probably this one here, right? Sorry. So the local density of states. The local density of states, we usually measure it as the field enhancement in the near field. However, this is how each one of these modes separately emits into the far field. So what we did a mode decomposition, so like an eigenfrequency solution that was done numerically, and then obtained the fields around the structure and then exported them in the far field for each mode separately here. But the local density of states, it refers to how all this superposition of modes couples into the quantum emitter. I'm not sure if I'm clear.
Jose Angel, do you have anything else to add? Jose Antonio, sorry. Jose Antonio, perdón.
No, sorry. Can you hear me?
Yes.
Yes.
Yeah. Perfect. You explained the question. I was confused between the far field profile and the near field profile, probably. So
what I'm showing here.
Yes, maybe if you were showing the near field profile, then you can directly connect it to the LDOS probably, but not in this case, as you explained. So thank you.
Yeah. So basically, we wanted to see how does each mode, because they were seeing experimentally far field behavior like this, and we're not really understanding where it was coming from. And it is a superposition of many modes emitting in a different way. Mm-hmm. And we wanted to decompose how each mode emits into the far field in order to be able to see which are the modes that they contribute into this profile.
Okay, thank you. Great. Mm-hmm.
Okay, so since the time is up, then we need to move on to the next and last speaker. Thank you very much, Angela, again, for your commitment to this online conference and for your very nice talk. So we move on to the last speaker of this session. This is going to be a contributed talk by Roberto Otero from the Universidad Autónoma de Madrid, who is going to talk about unveiling the radiative local density of optical states of a plasmonic nanocavity by STM. Thank you very much.
Okay, so thank you very much. I guess that you all can see my screen now and my image, hopefully, as well, although that's not so important. So what I'm going to be discussing today is about how one can use scanning tunneling microscopy in order to learn something about the optical properties of plasmonic nanocavities. This is a collaboration between us at Universidad Autónoma and IMDEA Nanoscience, who do the experiment, and the group of Garcia Vidal, who is giving the theory. And our question is actually a very theoretical question. It's basically the idea of how can we truly learn something about optics with STM. Now, why would we like to use STM to learn something about optics? Well, the main idea is that at the end of the day, the junction, the tunnel junction between the tip of an STM and a metallic sample is a nanocavity. It's a plasmonic nanocavity, like the nanoparticle mirror that we just saw before, right? From that point of view, it's also going to show extreme field enhancement, and therefore it could be used to investigate coupling to further quantum emitters that you place in between, and so on and so forth. And it has one important advantage, and it is that since this is an STM, we can modify both the distance between the tip and the sample with picometer resolution and the lateral position. So we can choose whether we stay on top of a single molecule, on top of a metallic sample, or anything like that, right? So all this would be very interesting if we really knew exactly what we were measuring when we measure luminescence induced by STM. While it is clear since the 70s, actually, that inelastic tunneling is involved in the excitation of localized plasmonic modes, so that electrons flow between, say, the tip and the sample. They lose a little bit of energy in between, and this energy is actually used to excite the localized surface plasmon resonances, which later on decay radiatively. It is also known, at the very least since 2010, more or less, that the electronic properties of tip and sample are very important. You can see that in this simple sketch, right? If you apply a bias voltage between the tip and the sample, you shift the Fermi levels of tip and samples. Therefore, you shift the electronic density of states of tip and sample, and therefore you change the availability of initial and final states for the inelastic tunneling process. So at the end of the day, what you get is a convolution, if you like, of optical, purely optical, and electronic properties. So what we would like to find out is a method to eliminate all these electronic contributions and be left completely with the optical characterization of the cavity. So this is how we do it. It's relatively easy to draw. It's not so easy to actually build it. We have a low temperature scanning tunneling microscope working at 4K. We have placed a lens relatively close from the place in which we are going to make the junction between the tip and the sample, and then we have an optical system outside of the vacuum chamber that leads to the spectrometer, and there we can actually measure the light spectra. You can have all the technical details in the thesis of my former student Alberto Martín Jiménez. This is actually what you measure. So you bring your tip, in our case it's an electrochemically etched gold tip, to a metallic sample. In our case it's a silver surface with a 111 orientation. We bring it, let's say, about 1 nanometer away from the substrate. You inject current, and then some light comes out, and you are able to collect this light as a function of the tunneling parameters. In particular, what I'm showing here is a stack of all the plasmonic spectra as a function of the bias voltage between the tip and the sample. Now, it has to be remembered at that point that we usually carry out our experiments by keeping our tunneling current constant. That means that if we increase the bias voltage, therefore, in order to keep the current constant, we need to decrease the conductance. And in order to decrease the conductance, we need to take the tip far away from the sample, right? So each voltage here corresponds to a different tip surface distance, and therefore corresponds to a different cavity, if you want to say it like that. And the higher the voltage, the larger the distance. You can see that there's a lot of action in the spectra, right? So to start with, there's something like an emission threshold. The emission threshold corresponds to the bias voltage that I'm applying. And that kind of makes sense, right? Because the bias voltage separates the occupied states from the unoccupied states. So therefore, if you need to couple occupied states in one electrode to unoccupied states in the other electrode, you need one of them to be empty and the other one to be occupied, and that basically limits the maximum energy that you can have. But other than that, you can see that the height of the peaks, the peak ratios actually change. The overall intensity changes so that it starts growing and then it decreases at relatively high voltages. You can observe some shifts in the peaks, shifts of the order of several let's say 10 to 25 or even to 50 milli-electron volts. And then the question is, how many of these changes actually arise because of the fact that I'm changing the cavity every time that I am changing the voltage, or how many of these changes are actually related to the different accessibility of initial and final states when I change the voltage? That's actually the question that we would like to answer. We started collaborating with the group of Professor García Vidal, and basically what they did is to simulate the tip as a sphere of gold and the sample as just a flat silver surface. They place a dipole right in the middle, and then they basically try to calculate the radiated power with the same geometry as our experiments as a function of the energy, the radiated spectrum. What we can see is that for numbers that are relatively reasonable, the spectrum resembles quite a bit the experimental ones. So basically it shows a peak at around 2.5 and a lower peak at around 3. That's more or less what we have over here, although our experimental spectra are way richer than the theoretical ones. The low energy spectra correspond to the dipolar mode. The high energy peak corresponds to the quadrupolar mode. And basically what we see is that our results compare well with the radiated power, but not with the full photonic density of states. Basically, for the full photonic density of states, the weight of the quadrupolar mode would be much larger, and that's not something that we observe in our experiment. Now, one might think actually that to have a spherical tip or a spherical model for the tip is more or less like having a spherical model of a cow. And if we actually have some ideas about that, and I would be happy to discuss at the end if that's some of your interest. Now, what we have in mind, therefore, is that somehow we have some spectra that would be the true optical spectra, that somehow there should be a role for some, let's say, for the rate of possible inelastic transitions, and that the true spectra that we observe is somehow the product of them, of those two contributions, those two factors. Now, how can we sort of estimate the rate for inelastic transitions? Well, somehow it should be proportional to how many occupied states you have in one electrode, right? So that should be electronic density of states times the Fermi occupancy. Should be proportional to how many empty states you have on the other electrode. And that should be the density of states, of electronic states at the, say, sample times 1 minus the Fermi energy. And there should be some weight of the probability for this kind of tunneling process to occur. Now, the interesting part of the business is that if now we consider a hypothetical situation in which we modify the actual bias voltage that we apply by subtracting the photon energy, then we are actually aligning the initial and the final states in the tunnel process. That would make my tunnel process switch from inelastic to elastic. And the nice thing about the elastic processes is that we know how to calculate them. Basically, once again, it's just the density of states times the Fermi occupancy, the density of states times the fermion occupancy, and some weight in between. If you actually study or compare those two contributions, you see that they two are exactly the same if you modify, if your V bias star corresponds to V bias minus the photon energy. Now, what does that mean? It means that if I want to know what would be the rate of inelastic excitations for one particular photon energy where I'm applying one particular bias voltage, what I should do is to subtract the photon energy from the bias voltage and measure the tunneling current at this modified voltage. And if I do the same thing at a different voltage, then same thing. So if I measure the IV curves of my tunneling junction, I can calculate the rate of inelastic tunneling as a function of the photon energy simply by reverting the curves and shifting the zero to the applied bias voltage, right? That, let me show how it works. So therefore, we have here the optical spectra for this tunnel junction recorded at 3 different stabilization voltages. We have here the IV curves recorded at the same stabilization voltages. So I take these IV curves, I flip them back in energy, I shift the zero to the applied bias voltage, and the first thing that you can see is that indeed the overall intensity kind of scales with the tunneling intensity that you would obtain by doing so. Moreover, if now I divide the experimental spectra by these IV curves, what I obtain are spectra that are much more similar to each other than they were before normalization. As a matter of fact, as you can see here, the global effect on all the different voltages that we have actually measured. You can see that now, while there's still a slight intensity increase for higher voltages, pretty much nothing else changes. So peak ratios are the same. Peak shifts have been reduced by quite a lot, but now they correspond well with the calculations from theory, whereas they didn't do so before. And what I'm doing here is comparing the shift of the low energy mode with the shift of the high energy mode. And I'm doing that because in principle, it's difficult for me to know what's the actual tunneling distance that I have. But if I actually make an effort to analyze this distance by measuring the slopes, the zero bias slopes of the IV curves, I can sort of plot the shifts in the low energy and high energy peaks as a function of the tip surface distance. And you can see how after normalizing the spectra, they correspond pretty well with theory, whereas they wouldn't correspond pretty well with theory before. So with all these, I think that we have shown, well, first of all, that indeed an STM junction is a tunable, or is very similar to a tunable nanoparticle on a metal plasmonic cavity. That what STM actually measures is the radiative photonic, or if you like, the radiative component, or radiative contribution to the photonic density of states in the plasmonic gap. We have shown how the actual spectra is composed of 2 different factors, a factor containing information about the electronic structure and a factor containing information only about the optical properties. And therefore, we can remove the influence of the electronic properties and be left only with the optical properties. And that opens a lot of interesting questions, such as, for example, now that I truly know what I'm measuring, and in particular, now that I truly know how to avoid all these problems with the electronic factors, I could actually place molecules in between, I could place 2-dimensional materials, I could place graphene nanoribbons and so on and so forth, and study their effects on the plasmonic response of the cavity in an individual way. We actually got these results published recently. You can actually check for further details there and in the supporting information. And being this talk at the intersection between STM and optical properties, there is one person I would have loved to have a long, interesting discussion about all these topics. And this person is my good friend, Juan Jose Sáenz Mole. We didn't have the time. So this is just for well, let's say in his memory. So with this, I come to the end of my talk. Thank you very much for your attention and for bearing with me to the very end.
Okay, thank you very much, Roberto, for this very nice talk, beautiful work. And this talk is now open for discussion. Any questions? Yes, from Antonio Garcia Martin. I read, nice job. Thanks for the talk. Maybe I missed it, but if you are in the tunnel regime, could one assume that the dielectric properties of the gap are different from a vacuum? How would this affect the theoretical results?
Absolutely. I mean, that's actually a very good point. As a matter of fact, what we believe is that we are pretty much in the edge of the, let's say, how plausible it is to apply this kind of theory, right? According to our calculations, we are, our measurements, we are, let's say, at about 1 nanometer. According to the calculations, we observe things that don't make sense and probably reflect non-local effects due to the fact that we are not using the proper theory at about, let's say, 0.5 nanometer or something like that and below. So we believe that we are very much at the edge. If we push our tip a little bit further, we should be able to observe these effects, which on the other hand would be interesting from the, let's say, from the fundamental point of view anyway.
Mm-hmm. Thank you. Any other questions? Well, maybe I can just ask one. In this conclusion, well, in this outlook, better said, when you say, can we address these modifications in plasmonic properties? No, well, I understand that this has so far not been done. No, as is it more posed like a think of the future, but are they maybe not by you, but from somebody attempt to characterize these properties in the way you do?
Well,
and to what extent it is the, you know, the technique sensitive enough or you know?
Right. If you place something in between the tip and the sample by placing some molecules in between, you have two different possibilities. The first possibility is that you place the molecule directly in contact with one of the metallic electrodes. In this case, the main problem is that there have been, of course, people trying to measure the plasmonic response depending on whether you inject on the molecule or you inject somewhere else. But the truth is that nothing is very clear. And we believe that nothing is very clear because when you inject through the molecule, the electronic structure changes completely. So only by following a normalization approach like the one that we are proposing here, I would expect to see anything that truly makes sense from the optical point of view. So if you have a look at the literature, you're going to find people who claims that the intensity increases or that the plasmonic intensity decreases or that it red shifts or that it blue shifts. It's not very clear what they have truly measured. I would say that after our work, I have some doubts as to whether they are not just measuring electronic properties and not truly optical properties. There's an alternative scenario, and it is that you intercalate some other dielectric. Like, for example, you place some few layers of salt on top of the silver layer, and then you place the molecule on top. That has been done, and it has the very interesting property that then, depending on the molecule and whether everything works fine and so on, but in principle, you're able to see excitonic emission. So you see much narrower peaks, even with few bands at lower energy that more or less correspond, or they are thought to correspond to Raman replicas of the main peak. So it's a lot of interesting work to be done. The mechanism for this excitonic emission is not very clear. Even more taking into consideration that usually you only use 2 or 3 atomic layers of salt, because of course you want to tunnel through it. So you are very, very close, not very clear why your molecule is not quenched, although after the previous talk, one might have some idea that this should indeed be the case. There's a lot of phenomenology and a lot of work to be done, and a lot of things that are not understood. So our hope is that we are bringing some light as to how to properly interpret these results.
Okay, thank you very much. So I don't see any other questions in the chat. So no, nothing, no hands raised. Okay, then with this I would thank you, Roberto, again for your talk, and close the session. Also thanking all the participants, the speakers, as well as the people in the audience. And now, please, before leaving, let's switch all of our cameras on for a picture that Pablo, I believe, is going to take of all of us.
Yes.
So Pablo, let us know when we need to start smiling.
Switch on your cameras, please. Okay, I will take one picture. Done. Thank you so much.
Okay, so thank you very much for this. And just a quick reminder that tomorrow the second session of this meeting colloquium will take place, same time, 9:30, more interesting talks. And at the end of the talks, there will be also the discussion of the pre-recorded talks and the posters. So you are welcome to attend. So see you all tomorrow then. Thank you.
Thank you. Bueno, todo funcionó bien, ¿no, Arantxa?
Sí, estaba esperando a ver si eso parece, ¿no?
Ha salido todo bastante bien.
Bien, bien. Sí, o sea que yo creo que, bueno, por suerte.